Let's dive into the basic neural networks with TensorFlow. Let's first start with building a simple feed-forward neural network. This is a 10-step process, so it's pretty easy. It might sound confusing because of the names, but let's go dive into it. Building a simple feed-forward neural network involves several steps, including defining the architecture, specifying the input and output layers, configuring the hidden layers, selecting activation functions, specifying the loss function and optimization algorithms, and training the model. Here's a step-by-step guide for building a simple feed-forward neural network using TensorFlow. So first thing, import the TensorFlow. Start by importing the TensorFlow library, which provides tools and functionalities for building and training neural networks. We say import TensorFlow STF. Next, define the architecture. Deciding on architecture of your neural network, including the number of input features, the number of hidden layers, the number of neurons in each hidden layer, and the number of output classes for classification tasks. Here is an example. What you do is input size equal to 784, hidden size 124, output size equal to 10. Now, when you say input size 784, there's a number of input features, example pixels in an image. Hidden size is 128, number of neurons in the hidden layer. Output size 10 is number of output classes, example digits 0 to 9. Next step is specify the input and output layers. You define the placeholders for the input data X and the corresponding labels Y if you are working on a supervised learning task. You say do this like this, X equal to tf.placeholder. Provide the way tf.float32 is what I'm using, shape equal to none, input size. Y equal to tf placeholder tf float, shape none, and output size. Step number 4 is configure the hidden layers. Define the hidden layers of your neural network, specifying the number of neurons and the activation function for each layer. You can do that by saying hidden layer equal to tf.layerDense, inputs equal to X, units equal to hidden size, and activation is tf.nn.relu. Step number 5 is specify the output layer. Define the output layer of the neural network which produces the final predictions. The output layer typically has no activation function for regression tasks but uses softmax activation for classification tasks. Example is output layer equal to tf.layers.dense, so input equal to hidden layer, units equal to output size. Step 6 is define the loss function. Specify the loss function that measures the discrepancy between the predicted outputs and the actual labels by saying loss equal to tf.reduceMean, and the first parameter is tf.nn.softmax underscore cross entropy underscore width underscore logits, and you provide labels equal to y and logits equal to output layer. Step 7 is select the optimization algorithm. In this, choose an optimization algorithm to minimize the loss function and update the model parameters, weights, and biases during training. Here is an Adam optimizer for gradient descent. Optimizer equal to tf.train.adam optimizer. Learning rate is 0.001. Next is train op is optimizer.minimize loss. Step number 8 is initialize variables. Before training the model, initialize the variables using a TensorFlow session. You can say init equal to tf.global variables initializer. Then with, so starting a session, you can say with tf.session ss/run init. Step number 9 is train the model. Run the training loop to optimize the model parameters using the specified optimization algorithm and loss function. In this example, here is an example training loop to replace with your data. For epoch in range, number of epochs, perform forward and backward pass. You can do that by saying current loss equal to session.run train op loss comma feedback feed dictionary equal to x input data and y is target labels. Print the training loss by saying print epoch plus 1 and loss equal to current.loss. Step number 10, the last option, is evaluating the model. This is an optional step. After training the model, evaluate its performance on a separate validation or test dataset to assess its accuracy and generalization ability. You can do that by saying accuracy equal to session.run. You pass the accuracy operation as the first input, then feed dictionary equal to x test data and y equal to test labels. print the test accuracy, and you'll get the accuracy options. By following these steps, you can build a simple feed-forward neural network using TensorFlow. Experiment with different architectures, activation functions, loss functions, and optimization algorithms to optimize the performance of your model for specific tasks. Adjust the hyperparameters such as learning rate and batch size to improve training efficiency and convergence. Activation functions. Activation functions play a crucial role in neural networks by introducing non-linearity, allowing neural networks to learn complex patterns and relationships in data. They are applied to the output of each neuron in a neural network, transforming the input signal into the output signal that is passed to the next layer. Let's dig deeper into activation functions. The first one that we'll look at is linear activation function. The linear activation function simply passes the input unchanged, making it suitable for regression tasks where the output can be any real number. However, it's rarely used in hidden layers of neural networks due to its limited representational power. Mathematically, you'll write it as fx equal to x, or function of x is x. TensorFlow usage is output equal to tf.keras.activations.linear and pass the input there. Next one is the sigmoid activation function. The sigmoid activation function squashes the input values between 0 and 1, which is useful for binary classification tasks where the output represents possibilities. Mathematically, you write it as function of x equal to 1 divided by 1 plus e raised to minus x. TensorFlow usage is output equal to tf.keras.activations.sigmoid and pass the input there. Hyperbolic tangent or tanh activation function. The hyperbolic tangent tanh activation function squashes the input values between -1 and 1, making it suitable for hidden layers of neural networks where the input can be both positive and negative. Mathematically is represented as fx equal to e raised to x minus e raised to minus x divided by ex plus e raised to minus x. The TensorFlow usage is output equal to tf.keras.activation.tanh and pass the input to it. The rectified linear unit or ReLU activation function. The rectified linear unit activation function introduces non-linearity by outputting the input value if it's positive and 0 otherwise. ReLU is widely used in hidden layers of neural networks due to its simplicity and effectiveness in training deep networks. Mathematically, it's represented as f of x or function of x equal to max of 0, x. TensorFlow usage is output equal to tf.keras.activation.ReLU and pass the input to it. Next one is leaky ReLU activation function. The leaky ReLU activation function addresses the dying ReLU problem by allowing a small positive gradient when the input is negative. It helps prevent the issues of neurons becoming inactive during training. Mathematically is represented as function of x equal to x comma alpha minus x if x is greater than 0, otherwise it's alpha minus x. TensorFlow usage is output equal to tf.keras.layers.leaky ReLU alpha is 0.2 and pass the input to it. Next is softmax activation function. The softmax activation function is commonly used in the output layer of neural networks for multi-class classification tasks. It squashes the input value into a probability distribution over multiple classes, ensuring that the output sums to 1. Mathematically is represented as function of xi equal to e raised to xi divided by summation of e raised to xj. TensorFlow usage is output equal to tf.keras.activation.softmax and pass the input to it. So activation functions introduce non-linearity into neural networks, allowing them to learn complex patterns and relationships in data. By understanding the characteristics and mathematical properties of different activation functions, you can choose the most appropriate one for your neural network architecture and task. Experiment with different activation functions and monitor the impact on model performance during your training and evaluation. Loss functions and optimizers. Let's get the big guns out. So here, loss functions and optimizers are essential components of neural network training, responsible for measuring the model's performance and updating its parameters to minimize the loss. Let's explore these concepts in depth. The loss function quantify the discrepancy between the predicted outputs of the model and the actual labels or targets. They are used to evaluate the performance of the model during training and guide the optimization process. The common loss function looks something like this. So let's go over the mean squared error first, MSE. Measures the average squared difference between the predicted and actual values. Suitable for regression tasks, mathematically it is represented as MSE equal to 1 raised to n summation of I is equal to 1 to n, and you pass and inside that you give y of I minus y of I, which is predicted if you see from the cap, squared. So TensorFlow usage is tf.keras.losses mean squared error. Next one is binary cross entropy. Measuring the binary classification loss between predicted probabilities and binary labels 0 or 1. Mathematically, binary cross entropy is represented by minus 1 raised to n summation of I is to 1 to n with yi times log of yi predicted plus 1 minus y of I into log of 1 minus y of I predicted value. TensorFlow usage is tf.keras.losses.binary cross entropy. Categorical cross entropy measures the multi-class classification loss between predicted probabilities and one hot encoded labels. Mathematically, the categorical cross entropy is represented as minus 1 raised to n from summation of I is 1 to n for summation of j of I to m y of ij log of y of ij predicted value. TensorFlow usage is tf.keras.losses.categorical cross entropy function. Next one is sparse categorical cross entropy. Similar to categorical cross entropy but accepts integer labels instead of one hot encoded labels. Mathematically, the sparse categorical cross entropy is represented as minus 1 upon n summation of I equal to 1 to n log of y of I, which is predictive value in the bracket of into the index of y of I. TensorFlow usage is tf.keras.losses.sparse_categorical cross entropy. Optimizers. Optimizers are algorithms used to minimize the loss function by updating the model's parameters, weights and biases during training. They adjust the parameters in the direction that reduces the loss, thereby improving the model's performance. Common optimizers are stochastic gradient descent, which is SGD, updates the parameters based on the gradient of the loss function with respect to each parameter. It is basic optimization algorithm used in neural network training. TensorFlow usage is tf.keras.optimizers.sgd, learning rate equal to 0.01. Next is ADAM, which you probably heard about before. This is the adaptive moment estimation. That's what ADAM stands for. Combines the advantages of both ADA grade and RMS prop algorithms. It adapts the learning rate for each parameter and uses momentum to accelerate training. TensorFlow usage is tf.keras.optimizers.adam and learning rate equal to 0.001. RMS prop, which we saw above. Root mean square propagation. That's what RMS prop stands for. This adjusts the learning rate for each parameter based on the magnitude of recent gradients. It prevents the learning rate from decreasing too fast for frequently occurring parameters. How do you use it in TensorFlow? tf.keras.optimizers RMS prop learning rate of 0.001. ADA grade, adaptive gradient algorithm. That's ADA grade. Adapts the learning rate for each parameter based on the historical gradients of that parameter. it allocates more learning to less frequently occurring parameters. TensorFlow usage is tf.keras.optimizers.add a grade learning rate of 0.01. Now, custom loss function and optimizers. You can also define custom loss functions and optimizers tailored to specific tasks or requirements by subclassing the appropriate TensorFlow classes and implementing the desired functionality. Here is an example of you can create a class of custom loss by passing tf.keras.losses.loss. You define initialize a self by saying super custom loss self. These are the constructors, and then call function where you pass the self y true y pred and return loss value. Custom loss equal to custom loss function. Custom optimizer equal to tf.keras.optimizers Adam learning rate of 0.001. Loss functions quantify the discrepancy between predicted and actual values, guiding the optimization process during training. Optimizers adjust the model's parameters to minimize the loss, improving the model's performance over time. By understanding different loss functions and optimizers and selecting the appropriate ones for your task, you can effectively train neural networks and achieve optimal results. Experiment with different combinations of loss functions and optimizers to find the best configuration for your specific problem. Let's get into the intermediate level of TensorFlow in this part 3. Now, the first topic that we have is customizing models with Keras, where we're going to look at introduction to Keras API. The Keras API is a high-level neural network API written in Python and capable of running on top of TensorFlow, Theana, or Microsoft Cognitive Toolkit, CNTK. It allows for easy and fast prototyping of deep learning models and is widely used for building and training neural networks. Let's delve into the introduction to the Keras API. So first, let's look at the overview of the Keras API. It's the high-level API. Keras provides a high-level, user-friendly interface for building, training, and deploying deep learning models. Keras enables easy construction of complex neural network architecture by providing a modular approach with building blocks like layers, activations, optimizers, etc. Keras supports multiple backends, hence the compatibility, including TensorFlow, Theano, and CNTK, making it flexible and versatile. Some of the key components of Keras API is layers. Keras provides a wide range of predefined layers for building neural networks, including dense, fully connected, convolutional, recurrent, dropout, etc. Activations. Keras supports various activation functions such as sigmoid, tanh, relu, softmax, etc., which introduce non-linearity into the network. Loss functions. Keras offers built-in loss functions for common tasks like regression, mean square error, binary classification, which is the binary cross entropy, and multi-class classification, which is the categorical cross entropy. Optimizers. Keras includes popular optimization algorithms like SJD, Adam, RMS prop, etc. for training neural networks effectively. Metrics. Keras provides built-in metrics to evaluate model performance during training, such as accuracy, precision, recall, etc. Callbacks. Keras callbacks allows for customizable actions at various stages of training, such as model checkpointing, early stopping, learning rate scheduling, etc. Example of building a neural network with Keras. Here is a simple example of building a neural network for image classification using the Keras API. In this, you'll probably see first I'm importing the TensorFlow STF. Next, I'm using from TensorFlow.Keras, I'm importing sequential. Then from TensorFlow Keras layers, I'm importing flatten and dense. Next, we define the model architecture by saying model equal to sequential, flatten of input shape equal to 28 by 28. Next, we have the input layer. What we did above is input layer flatten 28 by 28 images. Next, we're using dense 128 activation ReLU, where the hidden layer with 128 neurons and ReLU activation. Next, we're doing dense 10 activation softmax, where the output layer with 10 neurons for 10 classes and softmax activation. Next, we compile the model by calling the compile function and pass the optimizer as Adam, loss as sparse underscore categorical cross entropy, and metrics as accuracy. Then you print the model summary, and you'll see the model summary printed by giving model.summary. Let's look at training a neural network with Keras. Once the model is defined and compiled, you can train it using the fit method by providing the training data and labels. If you see here, how do you train the model? By calling the fit function and pass the train images, train labels, epochs equal to 10, batch size equal to 32, and validation data equal to val images and val labels. Next is evaluating and predicting with Keras model. After training, you can evaluate the model performance on a separate validation or test data set using the evaluate method. You evaluate the model by giving loss and accuracy equal to model.evaluate, pass the test images and the test labels, and then print test loss by loss and print test accuracy to accuracy. It's a tuple that you get back. That's why we have both the variables used together. Then you make predictions by saying predictions equal to model predict and pass the test images. The Keras API provides a user-friendly and versatile interface for building, training, and deploying deep learning models. By leveraging its modular components, you can quickly prototype and experiment with different neural network architectures, loss functions, optimizers, and more. Whether you're a beginner or an experienced deep learning practitioner, Keras offers a powerful toolset for developing state-of-the-art machine learning models. Let's go over building complex models with Keras. It involves combining various layers, activation functions, loss functions, optimizers, and other components to create neural networks tailored to specific tasks and requirements. Let's explore in more detail how to build complex models with Keras. The first, model architecture. Building complex models often requires designing architecture with multiple layers and connections between them. Keras allows the flexible construction of architectures using its sequential model or the functional API. Let's look at the example of a sequential model here. So from TensorFlow.js, I'm importing sequential. Then from TensorFlow keras.layers, I'm importing dense, con2D, max pooling 2D, and flatten. Then I create the model variable and pass it the sequential by passing the convo.td, having 32 parameters, kernel size is 3,3, activation is ReLU, input shape is 28 by 28 by 1. Next, we give the max pooling 2D pool size is 2 by 2. We give the convo.td 64, kernel size is 3 by 3, activation is ReLU, max pooling 2D for this is pool size 2,2. Then we flatten and then dense 128 activation ReLU, dense 10 activation softmax. Now compile this entire complex model by calling the compile function, and inside that we're saying optimizer is Adam, loss equal to sparse category cross entropy, and metrics equal to accuracy. Then you can print the model summary by calling the model summary function. And an example of a functional API looks something like this, where you first import model from TensorFlow Keras and then import con2D, max pooling 2D, flatten and dense from the Tensor Keras layers. Let's define the input layer by saying inputs equal to input shape of 28, 28, 1. Define the convolutional layers by saying con1 equal to con2D, 32, kernel size 3 by 3, activation ReLU, and pass the inputs. Pool 1 is max pooling 2D, give the pool size equal to 2 by 2 and conv1. For conv2, we say conv2D 64, kernel size 3 by 3, activation ReLU, and pass the pool 1. And for pool 2, max pooling 2D, pool size equal to 2 by 2 and pass the con2. Next, flatten the layers by calling the flatten function on pool 2. Next, we'll do the dense layers, where we call dense function with 128 activation ReLU and flatten, and dense function 10 with activation softmax of dense 1. Next, once we have that outputs, what we do is we define the model by calling the model function, pass the inputs in input and outputs to output. Next, we compile the model by calling the compile function, optimizer Adam, loss of same sparse categorical cross entropy, and metrics of accuracy. And then we print the model by calling model summary. Now, the next step is multiple inputs and outputs in this case. Complex models may involve multiple input or output branches. Keras allows you to handle such scenarios using its functional API by defining multiple input or output layers and connecting them appropriately. Shared layers. In some architectures, you may want to share certain layers between different branches of the model. Keras enables this by creating layers and reusing them across multiple parts of the model. Custom layers and loss functions. For more specialized tasks, you can define custom layers or loss functions by subclassing the appropriate Keras classes and implementing the desired functionality. Model subclassing. For maximum flexibility in building complex models, you can use model subclassing to define custom models with custom forward passes. This allows you to implement complex architectures and training loops from scratch. Now, building complex models with Keras involves leveraging its versatile capabilities, including the sequential model and functional API that we saw, the custom layers, loss functions, and more. By combining these elements creatively, you can design and train neural networks tailored to specific tasks and requirements, whether it's image classification, natural language processing, or other machine learning tasks. Experiment with different architectures and components to find the optimal configuration for your problem domain. Training and evaluating models. Now, training and evaluating models involve a series of steps, including preparing data, defining the models, compiling it, training with the training dataset, and evaluating its performance with validation or test data. Let's explore these 7 steps in more detail. The first step, data preparation. Before training a model, you need to prepare your data. This involves loading, pre-processing, and splitting the dataset into training, validation, and test sets. Let's look at an image classification example. In here, I'm importing the MNIST from TensorFlow Keras datasets. I'm importing 2 categorical from the Keras utilities, and I'm importing train test split from the model selection from sklearn. Now we load and pre-process the MNIST dataset. So for that, we say xtrain, ytrain, then use the xtest, ytest equal to mnist.load data. To xtrain, we pass xtrain.reshape by passing the variables of -1, 28, 28 by 1, and as type of float 32 and divide that by 255. Next xtest, we pass the reshape with -1, 28, 28, 1 as type of float 32 and divide that by 255. Next, we give ytrain to categorically ytrain and with the parameter of 10, and then ytest to categorically with ytest with the parameter of 10. Now split the data into training and validation sets by calling xtrain, xval, ytrain, yval, and then train the test split, call the train test split function and pass it the xtrain values from above, ytrain test size of 0.2 and random state of 42. Second step is defining the model. Now define the architecture of your neural network using Keras layer. This includes specifying the input layer, hidden layers, and the output layers. One of the examples that I've built here is first import the sequential from Keras. Next is con2d, max pooling 2d, flatten and dense from the layers. And then you can define a simple convolutional neural network by calling the sequential function and passing it that con2d of 32, kernel size 3 by 3, activation of ReLU and input shape of 28, 28, 1, max pooling 2d pool of 2 by 2, flatten that, and then dense 128 of activation ReLU and dense 10 of activation softmax. Next step is compiling the model. Compile the model by specifying the optimizer, loss function, and metrics to be used during training. Here's the example. So compile, you pass the optimizer of Adam, you pass the loss function of categorical cross entropy, and you pass the metrics of accuracy. Then next, train the model. Train the model using the training data and optionally a validation data set. Specify the number of epochs and batch size example. So in this case, if you look at the history, equal to model.fit xtrain, ytrain, epochs of 10, batch size of 32, validation data xval, yval. Fifth step is to evaluate the model. Evaluate the model performance on a separate test dataset or validation data to assess its accuracy and generalization. Example is here where we pass test loss, test accuracy is model.evaluate x test and y test, and the print the test loss and print the test accuracy. Sixth step is to visualize training history. In this, you can visualize the training history including loss and accuracy over epochs using the information collected during training. Here is an example where I can use the PLT from the matplotlib pyplot visualization tool. Plotting this particular training history, you use the PLT which we defined above and pass call the plot function and pass history.history loss and label of training loss. Then plot the plot history.history value loss and label. So you're plotting the training history across different axes and passing x label, y label for epoch and loss, and creating the legend using the legend function and plot the entire data into this plot.show function. Next step is making predictions. Once the model is trained, you can use it to make prediction on new data. Here's an example where you can say predictions equal to model predict and pass the new data to it, and it will make the predictions for you. Training and evaluating models involve a sequence of well-defined steps from data preparation to model definition, compilation, training, evaluation, and visualization. By following these steps, you can efficiently build, train, and assess the performance of neural networks for various machine learning tasks. Experiment with different architectures, hyperparameters, and training strategies to optimize the model's performance on your specific problem.
The next important topic is convolutional neural networks. Let's go over the introduction to CNNs. Convolutional neural networks, CNNs, are a class of deep neural networks designed to process and analyze structured grid-like data, such as images. They have revolutionized the field of computer vision and are widely used in tasks such as image classification, object detection, and segmentation. Let's delve deeper into the introduction to CNNs. So let's go over the basic concepts of CNN first. Some of the main key parameters in this concepts are the convolutional layers. Convolutional layers apply convolution operations to input data, extracting features through learnable filters or kernels. These filters capture spatial pattern in the input. Next one is the pooling layers. Pooling layers downsample the feature maps produced by convolutional layers, reducing their spatial dimensions while retaining important information. Common pooling operations include max pooling and average pooling. Activation functions. Nonlinear activation functions such as ReLU, rectified linear unit, which we have seen before, are applied after convolutional and pooling layers to introduce nonlinearity into the network and enable it to learn complex patterns. Then the last one is fully connected layers. After several convolutional and pooling layers, fully connected layers are added to the network to perform classification or regression based on the learned features. The second topic is convolution operation. The convolution operation involves sliding a filter, also known as a kernel, over the input data and computing the element-wise multiplication between the filter and the corresponding input patch, followed by summation. This process extracts spatial features from the input. Next one is the convolutional layer. A convolutional layer consists of multiple filters that slide over the input data, each producing a feature map by convolving with the input. These feature maps represent different learned patterns or features present in the input. The pooling operations. The pooling layers reduce the spatial dimensions of feature maps by downsampling. Max pooling, for example, selects the maximum value within each pooling window, while average pooling computes the average value. Let's go over the architecture of CNNs. CNN architecture typically consists of alternating convolutional and pooling layers, followed by fully connected layers for classification or regression. Modern architectures such as the VGG, RESTnet, and Inception are deeper and more complex, achieving state-of-art performance on various tasks. How do you train CNNs? So training CNNs are trained using gradient-based optimization algorithms such as stochastic gradient descent, which is SGD, ADAM, or RMS prop, which we saw before. The loss function measures the discrepancy between the predicted outputs and the actual labels, and backpropagation is used to update the network's parameters like weights and biases to minimize the loss. Next, transfer learning. Transfer learning is a common technique in CNNs where pre-trained models trained on a large dataset, example ImageNet, are fine-tuned on smaller datasets or specific tasks. This approach leverages the learned features from pre-trained models and adapts them to the new task, often leading to improved performance with less data. What are the applications of CNN? CNNs have applications in various domains, including image classification, object detection, facial recognition, medical image analysis, autonomous vehicles, and more. They have demonstrated remarkable performance in tasks requiring understanding and processing of visual data. So convolutional neural networks have transformed the field of computer vision and are the cornerstone of many state-of-the-art algorithms for image analysis and understanding. Understanding the fundamental concepts, architecture, and training procedures of CNN is essential for effectively applying them to real-world problems and achieving superior performance in visual tasks. Experimenting with different architectures, hyperparameters, and trained strategies can further enhance the capabilities of CNN for specific applications. Let's go over building and training CNNs with TensorFlow. Now, building and training convolutional neural networks CNNs with TensorFlow involves using its high-level APIs Keras, which provides a user-friendly interface for constructing and training deep learning models. Let's delve deeper into the process of building and training CNNs with TensorFlow. First step, import TensorFlow and Keras. Starting by importing TensorFlow and the necessary modules for Keras, we do if you see here in this example, we are first importing TensorFlow SDF. Now from Keras we are importing sequential, and from Keras layers we are importing conv2D, the convolution, max pooling 2D, and flatten and dense. Next step, we define the architecture of your CNNs by stacking convolutional and pooling layers, followed by fully connected layers for classification. So that's why we use the sequential algorithm architecture, and we use the conv2D, max pooling TD, conv2D, max pooling, then flatten, and then dense with the two parameters 128 activations of ReLU and 10 and activation of softmax. This is something that we've done before, but this is more into the details of it. Next, we compile the model. We compile the modeling by specifying the optimizer, the loss function, and the metrics to be used during training. So if you see here, we use the model.compile, optimize using ADAM, loss is using sparse categorical cross entropy, and metrics is accuracy. Next, we load the pre-processed data. Load and pre-process your data set. For example, if you're working with image data, you may need to resize the images and normalize pixel values. You do that by xtrain ytrain and then xtest ytest is equal to tf.keras.datasets.mnest load data, where we're taking the data from the mnest. Then we are xtrain equal to xtrain.reshape. You're giving the parameters, or you want to shape it as float divided by 255. Same thing for xtest, with xtest.reshape, give the parameters and as type float 32 about divided by 255. Next step is training the model. Train the model using the fit method, specifying the training data, number of epochs, and batch size. So if you see here in this example, model.fit, we give the xtrain ytrain, then epochs is 10, batch size of 32, validation split is 0.2. Lastly, evaluating the model. Evaluating the model's performance on a separate test data set to assess its accuracy and generalization. So I say test loss test accuracy tuple, which I can get from model.evaluate xtest ytest, and then I can print the test loss, and test accuracy. Building and training CNNs with TensorFlow is made straightforward with the Keras API. By following these steps, you can quickly construct, compile, train, and evaluate CNN models for various computer vision tasks. Experiment with different architectures, hyperparameters, and training strategies to optimize the performance of your CNNs for specific applications. Additionally, consider techniques such as data augmentation, regularization, and transfer learning to further improve model performance and robustness. Transfer learning with pre-trained CNNs. Transfer learning with pre-trained CNNs is a powerful technique that leverages knowledge learned from large datasets to improve the performance of models on tasks with limited data. In this approach, a pre-trained CNN model trained on a large dataset such as ImageNet is used as a feature extractor or as a starting point for training on a new data set or specific task. Let's delve deeper into transfer learning with pre-trained CNNs. First topic is all about overview of transfer learning. Transfer learning involves transferring knowledge from a source domain, usually a large data set, to a target domain, a smaller data set, or a specific task. In the context of CNNs, this typically means using the learned features from pre-trained models to improve the performance of models on new tasks. The second one is benefits of transfer learning. First one is improved performance. Pre-trained models have learned rich feature representations from large dataset, which can generalize well to new tasks. Second is faster training. Transfer learning often requires less data and training time compared to training from scratch, as the model starts with pre-learned features. Third one is robustness. Pre-trained models have been trained on diverse datasets, making them more robust to variations and noise in the data. The third part that we'll go over is the transfer learning strategies. There are two common strategies for transfer learning with pre-trained CNNs. First one is the feature extraction. In this approach, the pre-trained CNN model is used as a fixed feature extractor. The convolutional base of the pre-trained model is frozen, and only the fully connected layers or a few additional layers are added and trained to the new dataset. Fine-tuning. In fine-tuning, the pre-trained CNN model is used as an initialization for training on the new dataset. The convolutional base is fine-tuned along with the additional layers added for the new task. Fine-tuning allows the model to adapt the learned features to the specific characteristics of the new dataset. Fourth one, implementing transfer learning with TensorFlow Keras. Implementing transfer learning with pre-trained CNN in TensorFlow Keras involves the following steps. The first one is load pre-trained model. To load a pre-trained CNN model such as a VGG, RESTnet, Inception, or MobileNet using tf.keras applications is here as explained below. Base model is equal to tf.keras application VGG16. Now we pass these parameters which are weights, which ImageNet include top equal to false and input shape equal to 224 to 24 by 3, the parameters of the image set. Next step is feature extraction. Freeze the convolutional base of the pre-trained model and add custom fully connected layers on top of the new task. This is what you can do by saying first base model trainable equal to false, so you're freezing the model. Next, model equal to sequential, you pass the base model, you call the flatten function, you call dense function with 255 and activation equal to relu, and dense with 10 and activation equal to softmax. Next step is fine tuning. Fine tune the entire model or a subset of layers on a new dataset, optionally using a lower learning rate for the pre-trained layers. You do that by saying again base model.trainable equal to true. Fine tune at 100 for layers in base model.layers. So go over each and every one. Fine tune at use the parameter and then say layers.trainable equal to false. Next step is train and evaluate. Train the model on a new dataset and evaluate its performance on a separate validation or test dataset. You can do that by calling the compile method and pass it optimizer Adam, loss function equals parse, categorical cross entropy, and matrix is accuracy. Then you fit by calling the fit function, train the data set, give the epochs of 10, validation data is equal to validation data set. Next, test loss and test accuracy you can get from calling the evaluate function and pass the test data set. Fifth one is choosing the right pre-trained model. The choice of pre-trained model depends on factors such as the size and nature of the target dataset, computational resources, and the specific characteristics of the task. Experimentation with different pre-trained models and transfer learning strategies is often necessary to find the optimal solution. So transfer learning with pre-trained CNNs is a valuable technique for leveraging knowledge from large datasets to improve the performance of models on new tasks or datasets with limited data. By following the steps outlined above and experimenting with different pre-trained models and transfer learning strategies, you can effectively apply transfer learning to a wide range of computer vision tasks and achieve superior performance with less data and computational resources. Recurrent neural networks. Let's go with the introduction to the RNNs. RNNs or recurrent neural networks are a class of neural networks designed to effectively process sequential data by maintaining an internal state or memory. They are widely used in natural language processing, speech recognition, time series analysis, and other sequential data tasks. Let's deep dive into the introduction to RNNs. Some of the basic concepts of RNN are sequential data, temporal dependency, and vanishing gradient problem. RNNs are specifically designed to handle sequential data where the order of element matters. Examples include sentences in a natural language, audio signals, and time series data. The temporary dependencies, for that, RNNs maintain a hidden state that captures information from previous time steps, allowing them to model temporal dependencies in sequential data. What is the vanishing gradient problem? Traditional RNNs suffer from the vanishing gradient problem, where gradients diminish exponentially over long sequences, making it difficult to learn long-term dependencies. What is the architecture of RNNs? First one is the recurrent connections. RNNs have recurrent connections that allow information to persist over time by feeding the output of the network back to itself at the next time step. The hidden state. At each time step, RNNs maintain a hidden state vector that summarizes the information processed up to that point. Output. The output of an RNN at each time step can be used for prediction, classification, or as an input to subsequent layers in the network. The types of RNN. There are 4 types of RNN. First is one-to-one, traditional feed-forward neural networks that process fixed size input and produce fixed size output. One-to-many generate a sequence output based on a single input, example image captioning. Many-to-one produce a single output based on a sequence of inputs, example sentiment analysis. Many-to-many or sequence-to-sequence is process a sequence of inputs and produce a sequence of outputs, example machine translation. Long short term memory, LSTM, and gated recurrent units. LSTM or long short term memory networks are a variant of RNNs designed to address the vanishing gradient problem by introducing memory cells and gating mechanisms that control the flow of information. GRU or gated recurrent units are a simplified version of LSTM that also incorporate gating mechanisms but with fewer parameters. Training RNNs. The first way of doing that is backpropagation through time, BPTT. RNNs are trained using backpropagation through time, where the gradients are propagated backwards through the recurrent connections over multiple time steps. Next way training is gradient clipping. To mitigate the exploding gradient problem, gradient clipping techniques are often applied to limit the magnitude of gradients during training. Next training method is regularization. Techniques such as dropout and recurrent dropout can be used to regularize RNNs and prevail over fitting. What are the applications of RNNs? The first one is natural language processing. RNNs are widely used for tasks such as language modeling, sentiment analysis, machine translation, and named entity recognition. Next one is speech recognition. RNNs can process sequential audio data for tasks like speech recognition, speaker identification, and voice synthesis. Another application is time series analysis. RNNs are effective for modeling and forecasting time series data such as stock prices, weather patterns, and sensor data. Recurrent neural networks (RNNs) are powerful models for processing and analyzing sequential data thanks to their ability to capture temporal dependencies. Despite challenges such as the vanishing gradient problem, variants like LSTM and GRU have been developed to address these issues, making RNNs application to a wide range of tasks in the natural language processing, speech recognition, time series analysis, and beyond. Understanding the architecture, training techniques, and application of RNNs is essential for effectively applying them to the real-world problems and extracting meaningful insights from sequential data. Building and training recurrent neural networks (RNNs) with TensorFlow involves using its high-level APIs, Keras, which provides convenient abstractions for constructing and training RNN models. Let's delve deeper into the process of building and training RNNs with TensorFlow. So first step is mostly about importing TensorFlow and Keras. We start by importing TensorFlow and the necessary modules from the Keras by doing first import TensorFlow STF, then from the Keras models get sequential, and from Keras layers we'll get the simple RNN, LSTM, GRU, and DENS. Next step is define the model architecture. Define the architecture of your RNN model using Keras layers. Choose from simple RNN, LSTM, or GRU layers based on the complexity of your task and the presence of long-term dependencies in the data. One of the example using simple RNN is here. You can just say model sequential and call the simple RNN function and pass the attributes like 64, input shape equal to sequence length, and input dim and activation equal to ReLU. Then use DENS, num classes, and activation is equal to softmax. Next example using LSTM is you just call the LSTM method, pass the parameters 64 and input shape equal to sequence length and input dim. It doesn't need the activation, and pass the DENS as num classes and activation equal to softmax here. Next, using GRU, you can call the GRU function, same stuff, same as LSTM, and it looks exactly the same, just the name of the function is different. Next step is to compile the model using the compile function. So compile the RNN model by specifying the optimizer, loss function, and metrics to be used during training. So we pass the optimizer as Adam, loss function as categorical cross entropy, and metrics as accuracy. Next step is to load and pre-process data. Load and pre-process your sequential data. Ensure that your input data is properly formatted as sequences of fixed length, xtrain, ytrain, the two tuples, by calling load data and pass the train data path. Xtrain ytest equal load data and pass the test data path. Next thing is training the model. Train the RNN model using the fit method, specifying the training data, number of epochs, and batch size. You can call the fit method, pass the xtrain, ytrain, epochs is 10, batch size 32 in this case, and validation data is xtest and ytest. Last step is to evaluate the model. Evaluate the performance of the trained RNN model on a separate test data set. So you can get the test loss and test accuracy by calling the model.evaluate function and pass the xtest and ytest data. It will print out the test loss and test accuracy for you. So building and training recurrent neural networks RNNs with TensorFlow is made straightforward with the Keras API. By following these steps, you can quickly construct, compile, train, and evaluate RNN models for various sequential data tasks. Experiment with different RNN architectures like simple RNN, LSTR, GRU as we saw above, hyperparameters, and training strategies to optimize the performance of your models for specific applications. Additionally, consider techniques such as regularization, dropout, and gradient clipping
to improve the robustness and generalization of your RNN models. We learned about RNN, but now let's look at applications of RNNs, specifically at language modeling and time series predictions. So recurrent neural networks find numerous applications across various domains due to the ability to model sequential data and capture temporal dependencies. Two common applications of RNNs are language modeling and time series prediction. Let's delve deeper into each of these. So first, language modeling. Language modeling involves predicting the next word in a sequence of words given the previous words. RNNs are well suited for language modeling tasks because of their ability to capture dependencies between words in a sentence. Applications of RNN in language modeling include: first one is text generation. RNNs can generate realistic text by predicting the next word based on the context of previous words. This is commonly used in applications such as chatbots, virtual assistants, and automatic writing. And you've probably figured out where you have used it by now. Next one is machine translation. RNNs are used in machine translation systems to model the relationship between words in different languages and generate accurate translations. Next one is speech recognition. RNNs can model the temporal dependencies in speech data and convert spoken language into text, enabling applications like voice search and speech-to-text transcription. Sentiment analysis. For RNNs can analyze the sentiment of the text data by modeling the context and relationship between words in a sentence, enabling applications like sentiment analysis in social media and customer feedback analysis. The second application is in time series prediction. Time series prediction involves forecasting future values based on historical observations in a time-ordered sequence. RNNs are effective for time series prediction tasks because they can capture temporal dependencies and patterns in the data. Applications of RNN in time series prediction include the stock market prediction. RNNs can analyze historical stock price data and predict future stock prices, enabling applications like algorithmic trading and portfolio optimization. There's weather forecasting. RNNs can analyze historical weather data and predict future weather conditions, including temperature, precipitation, and wind patterns, enabling applications like weather forecasting and climate modeling. Demand forecasting. RNN can analyze historical sales data and predict future demands for products or services, enabling applications like inventory management, supply chain optimization, and resource planning. Healthcare forecasting. RNNs can analyze time series data from medical sensors and patient records to predict future health outcomes, enabling applications like disease diagnosis, patient monitoring, and personalized treatment planning. Recurrent neural networks are versatile models that find applications in a wide range of domains, including language modeling and time series prediction. By leveraging their ability to model sequential data and capture temporal dependencies, RNN enables various intelligent applications such as text generation, machine translation, speech recognition, stock market prediction, weather forecasting, demand forecasting, healthcare forecasting, and more. Understanding the principles and applications of RNNs is essential for effectively applying them in real-world problems and extracting meaningful insights from sequential data. Let's start with part 4. This is the advanced section of TensorFlow, where we'll be covering deploying TensorFlow models, distributed TensorFlow, and understanding TensorFlow extended TFX. So in the deploying TensorFlow models, let's go over those first, where we'll be saving and loading models, TensorFlow serving for model deployment, and TensorFlow Lite for mobile and embedded devices. Let's kick off with saving and loading models. Now, deploying TensorFlow models involves several steps, including saving trained models to disk and loading them for inference in production environments. Let's deep dive into the process of saving and loading TensorFlow models. The first step is saving models. After training a TensorFlow model, you'll want to save its architecture, weights, and optimizer state to disk for future use. TensorFlow provides multiple ways to save models. First one, save the entire model. You can save the entire model, including its architecture, weights, and optimizer state in a single file using the save method. You can just say model.save and give a name and save it as .h5 file.
Save a model architecture and weights separately. Alternatively, you can save the model architecture to a JSON or YAML file and save the weights to separate HDF5 files. You can do that by saying that first save model architecture to JSON file using with open model.js JSON and then w as JSON file and JSON file.write function and pass model to JSON function. Next, save model weights to HDF5 file. You can say model.save weights and give it a file name and give the extension h5. Next step is loading models. Once you have saved a TensorFlow model, you can load it back into memory for inference or further training. TensorFlow provides methods to load models saved in different formats. So load entire model. To load an entire model saved in a single HDF5 file, use the load model function. So whatever we did in the previous case for saving, we can load it by using from TensorFlow.keras models, import the load model module, and then you can call that load model function and just pass the HDF5 file that you have given. Next is load model architecture and weight separately, the ones that we saved separately. To load the model architecture from a JSON or YAML file, which we did in the previous step, and load the weights from a separate HDF5 file, use the following methods. So here, if you see, what I do is I'm importing model from JSON and then loading model architecture from the JSON file by calling with open function, where I am passing the model.json and I'm saying read a JSON file. Load the model, create a variable for loading the model and call the JSON_file.read function, and the loaded model is loaded into model from JSON and pass the load model_JSON here. Next, if you want to load the weights from HDF5 file, all you do is loaded model.load weights function and pass model weighted.h5 file. Model compatibility. When saving and loading TensorFlow models, ensure that you are using compatible versions of TensorFlow and Keras. Models saved with one version may not be compatible with other versions due to changes in the underlying API. So be careful about that if something is messed up because of that. Next step is model serialization options, where depending on your deployment environment and requirements, you may choose to serialize your TensorFlow models in a different format, such as HDF5, JSON, or protocol buffers, protobuf. Evaluate the pros and cons of each format based on factors like file size, interoperability, and ease of use. Saving and loading TensorFlow models is a crucial step in deploying machine learning models to production environments. By following the appropriate methods for saving and loading models, you can ensure seamless integration of your trained models into production pipelines and application. Consider factors like compatibility, serialization options, and deployment requirements when choosing the best approach for saving and loading TensorFlow models in your deployment workflow. TensorFlow serving for model deployment. TensorFlow serving is a flexible, high-performance serving system for deploying machine learning models in production environments. It simplifies the process of serving TensorFlow models over a network and provides features such as model versioning, monitoring, and scalability. Let's deep dive into deploying TensorFlow models using TensorFlow serving. It kind of consists of 7 steps. The first step is installation and setup. Start by installing TensorFlow serving on your server or deployment environment. You can install TensorFlow serving via Docker or by building it from source. For that, here is an example. You can say docker pull TensorFlow/serving. The second step is exporting TensorFlow models. Before deploying a TensorFlow model with TensorFlow serving, you need to export the trained model in the saved model format. This format includes the model architecture, weights, and metadata necessary for serving. So first import TensorFlow HDF, then you can call the Keras Keras.model.load model function and pass the h5 file, and then you can for using TensorFlow call the save model using save function and pass the model and the saved model in there. Next step is running TensorFlow serving. Start TensorFlow serving with the exported saved model. Specify the model name and version as well as port to expose for serving request.
This you can do by your docker run p port number 8501 dash name equal to TensorFlow serving, mount type equal to bind, comma source, and path to the saved model. Then target is model name, and next is the model name, where using the dash e parameter pass the model name, and by using the dash t TensorFlow serving. Next step is for serving request. Once TensorFlow serving is running, you can send inference request to it using HTTP or gRPC protocols. The model name and the version are specified in the request URL or headers. Examples of sending an HTTP request for inference: here you can call the curl method -d and pass the instances 1, 2, 3, 4, pass their values, and you can post it to, let's say if you're running on your localhost 8501/v1/model/model name and then predict. So this is how you can pass and get the request passed to the HTTP server. Next step is model versioning and updating. TensorFlow serving supports model versioning, allowing you to deploy multiple versions of a model simultaneously and switch between them seamlessly. This enables alpha beta A/B testing, gradual rollouts, and model updates without downtime. Next step is monitoring and management. TensorFlow serving provides monitoring and management capabilities through a web inference interface called as TensorBoard. You can monitor model performance, request latency, throughput, and other metrics in real time. Last step is scalability and performance. TensorFlow serving is designed for high performance serving of machine learning models at scale. It supports serving multiple models concurrently, load balancing, and distributed deployment for handling large inference workloads efficiently. TensorFlow serving is a powerful and scalable solution for deploying TensorFlow models in production environments. By following the steps outlined above, you can deploy trained TensorFlow models with TensorFlow serving inference requests over HTTP or gRPC protocols. With features like model versioning, monitoring, scalability, and performance optimizations, TensorFlow serving enables robust and efficient deployment of machine learning models for real-world application. Consider incorporating TensorFlow serving into your deployment workflow to streamline model deployment and management in production environments. Next, let's look at TensorFlow Lite for mobile and embedded devices. TensorFlow Lite is a lightweight and optimized framework for deploying machine learning models on mobile and embedded devices, enabling efficient inference with low latency and reduced memory footprint. Let's deep dive into deploying TensorFlow models using TensorFlow Lite for mobile and embedded devices. First one that we'll look at is conversion to TensorFlow Lite format. Before deploying a TensorFlow model to a mobile or embedded device using TensorFlow Lite, you need to convert the model to the TensorFlow Lite format. TensorFlow provides tools and APIs for converting TensorFlow models to TensorFlow Lite format. Example of conversion using TensorFlow Lite converter is right here, where we are first importing TensorFlow HDF, then load the trained tensor model using the load model function provided by the Keras models. Next, we are converting the models to TensorFlow Lite format by calling the from Keras model function and passing the model to it, which is part of the TF Lite converter, which is the TensorFlow Lite converter, passing it to putting it in the converter variable. Next, we are calling converter.convert and passing that model into the TF Lite model of instance. Now, once we're done with that, save the converted TensorFlow Lite model into a file by calling with open model.tflite file is the name of the file, and we're writing it to that as f, and we can say f.write tflite model, pass it that tflite model that we created up above. Next is TensorFlow Lite interpreter. To run the inference with TensorFlow Lite models on mobile or embedded devices, you'll use the TensorFlow Lite interpreter. This interpreter provides a C++ API for embedding TensorFlow Lite models into mobile apps and a Java API for Android apps. Examples of running inference with TensorFlow Lite interpreter using Python is here, where I am importing NumPy and TensorFlow. Next, I am loading the TensorFlow Lite model by calling this calling the interpreter function and passing the model path. Next, I am taking that interpreter and allocating tensors. Next, I am to get inputs and output tensors. What you do is put the create two variables, input details and output details, and from the interpreter I'm saying get input details and get output details function. Next, you prepare the input data by calling the np, the numpy, and create an array 1 with four parameters here, 4 parameters inside an array, and then call the pass the dt type equal to np.float32, so it's float, it knows that's float values. Next, I'm setting tensor for interpreter by calling the set tensor method and passing the input details to it at a particular index, and then I'm saying input data. Next, I am running inference by calling interpreter.invoke. Next, the output data you can get from the interpreter by calling the get tensor and give it the output details value with at 0 at index. So this will print out your output data that from this TensorFlow Lite interpreter. Third one is model optimization techniques. TensorFlow Lite provides various optimization techniques to reduce the size and improve the performance of TensorFlow Lite models for mobile and embedded deployment. These techniques include quantization, quantizing model weights and activations to lower precision, example 8-bit integers, to reduce model size and improve inference speed. The next one is model pruning, removing redundant or less important weights from the model to reduce model size without significantly affecting the accuracy. Next is operator fusion, fusing multiple operations into a single operation to reduce memory access and improve performance. Next one is selective execution, where what it does is optimizing the execution of TensorFlow Lite operators based on device capabilities and hardware accelerators. Deployment on mobile and embedded devices. Once you have converted and optimized your TensorFlow model to TensorFlow Lite format, you can deploy it on mobile and embedded devices such as smartphones, tablets, IoT devices, and microcontrollers. TensorFlow Lite supports various platforms including Android, iOS, Linux, Windows, and microcontrollers like Raspberry Pi. TensorFlow Lite is a powerful framework for deploying machine learning models on mobile and embedded devices, enabling efficient inference with low latency and reduced memory footprint. By converting, optimizing, and deploying TensorFlow models using TensorFlow Lite, you can bring the power of machine learning to a wide range of mobile and embedded applications, including image recognition, natural language processing, gesture recognition, and more. Consider incorporating TensorFlow Lite into your deployment workflow to deploy machine learning models effectively on resource-constrained devices and create innovative and intelligent mobile and embedded applications. TensorFlow's distributed execution framework. This framework enables the efficient distribution and coordination of computations across multiple devices or machines in a distributed setup. The framework is crucial for scaling machine learning tasks, accelerating computation, and handling large data sets efficiently. Let's dive deeper into the key concepts and features of TensorFlow's distributed execution framework. The first one is the distributed execution engine. TensorFlow's distributed execution engine manages the distribution and coordination of computations across worker nodes in a distributed setup. It includes several components and features to facilitate distributed training and inference. The first one is distributed sessions. TensorFlow provides distributed session objects tf.distribute.strategy that manage the execution of TensorFlow graphs across multiple devices or machines in a distributed setup. These sessions coordinate the placement of operations and tensors, handle communication between devices, and manage the synchronization of computations. Distributed optimizers. TensorFlow includes distributed versions of popular optimizers, example Adam and SGD, that are designed to handle distributed training scenarios efficiently. These optimizers implement techniques such as gradient averaging, gradient clipping, and asynchronous updates to optimize performance and convergence in distributed setups. Fault tolerance. TensorFlow's distributed execution engine includes mechanisms for handling failure and retries in distributed setups. It provides fault-tolerant communication protocols, checkpointing mechanisms, and recovery strategies to ensure that computations continue even in the presence of node failure or network issues. Second one is the distributed training strategies. TensorFlow supports various distributed training strategies to accelerate model training and handle large datasets. Some common distributed training strategies include data parallelism. In data parallelism, the dataset is partitioned across multiple devices or machines, and each device computes gradients independently using a subset of data. Gradients are then aggregated across devices to update the model parameters. TensorFlow's tf.distribute.mirror strategy is commonly used for data parallelism. Model parallelism. In model parallelism, different parts of the model are computed on different devices or machines. This is useful for large models that cannot fit into the memory of a single device. TensorFlow's tf.distribute.strategy provides support for model parallelism by allowing developers to specify custom devices placement and execution strategies. Pipeline parallelism. Pipeline parallelism divides the computation graph into stages, with each stage running on a separate device or machine. Data flows through the pipeline and computations are overlapped to improve throughput. TensorFlow's tf.distribute.strategy can be used to implement pipeline parallelism by partitioning the computation graph and coordinating the execution of stages across devices. The third one is deployment and configuration. Deploying and configuring distributed TensorFlow setup requires careful consideration of factors such as network topology, device placement, communication overhead, and resource allocation. TensorFlow provides tools and APIs for configuring and managing distributed setups, including tf.distribute.strategy. TensorFlow's distribution strategy API tf.distribute.strategy provides a high-level interface for distributing computation across devices or machines. It supports various strategies such as mirrored strategy, parameter server strategy, and multi-worker mirrored strategy, allowing developers to choose the most suitable strategy based on their requirement and deployment environment. TensorFlow Extended (TFX). TensorFlow Extended provides end-to-end tools and platforms for developing and managing production ML pipelines, including distributed TensorFlow setups. TFX includes components for data ingestion, pre-processing, training, evaluation, and serving, enabling developers to build and deploy scalable and reliable machine learning systems. TensorFlow's distributed execution framework is a powerful and flexible solution for scaling machine learning tasks across multiple devices or machines. By leveraging TensorFlow's distributed training strategies, execution engine, and deployment tools, developers can build and deploy distributed machine learning models for a wide range of applications, from training deep neural networks on large-scale datasets to deploying real-time inference services in production environment. Understanding the key components and features of TensorFlow's distributed execution framework is essential for effectively harnessing the power of distributed systems and scaling machine learning workflows to meet the demands of modern applications. Scaling TensorFlow with TensorFlow Serving and Kubernetes. Scaling TensorFlow with TensorFlow Serving and Kubernetes involves deploying TensorFlow models as scalable and reliable services on Kubernetes clusters using TensorFlow Serving. This allows for efficient serving of machine learning models, handling various levels of workload, and ensuring high-level availability and scalability. Let's dive deeper into the key concepts and steps involved in scaling TensorFlow with TensorFlow Serving and Kubernetes. Let's go first with TensorFlow Serving. TensorFlow Serving is a flexible, high-performance serving system for deploying machine learning models in production environments. It provides a platform-agnostic interface for serving TensorFlow models over a network and includes features such as model versioning, monitoring, and scalability. Key components and features of TensorFlow serving include servables. TensorFlow serving organizes models into servables, which represent the different versions of a model that can be served. Each servable is associated with a unique version number and can be loaded and served independently. Loaders. TensorFlow servers serving uses loaders to load and manage servables in memory. Loaders handle tasks such as model initialization, version management, and resource allocation. Predictors. Predictors are responsible for handling inference requests and generating predictions using loaded servables. TensorFlow serving supports various prediction APIs including gRPC, HTTP REST, and TensorFlow serving's native API. Let's look at Kubernetes. Kubernetes is an open source container orchestration platform that automates the deployment, scaling, and management of containerized applications. Kubernetes provides features such as service discovery, load balancing, auto-scaling, and self-healing, making it well suited for deploying and managing distributed systems at scale. Key components and features of Kubernetes includes pods. Pods are smallest deployable units in Kubernetes and encapsulate one or more containers. Each pod has its own IP address and resource allocation, making it a logical unit of deployment for containerized applications. Deployments. Deployments define the desired state of a set of pods and manage their lifecycle. Deployments handle tasks such as pod creation, scaling, rolling updates, and self-healing in response to failure or changes in resource requirements. Services. Services provide network connectivity to pods and enable communication between different parts of a distributed application. Kubernetes services abstract away the underlying network topology and provide a stable endpoint for accessing pods. Last one is scaling TensorFlow with TensorFlow serving and Kubernetes. To scale TensorFlow models with TensorFlow serving and Kubernetes, follow these steps. First, containerize TensorFlow models. Package TensorFlow models as Docker containers with TensorFlow serving installed. Define a Docker file to specify the model serving environments and dependencies. Next, deploy the TensorFlow serving on Kubernetes. Create Kubernetes deployment and service manifest to deploy TensorFlow serving instances as pods. Specify resource requirements such as CPU and memory limits to ensure efficient resource utilization. Next, expose TensorFlow serving service. Expose the TensorFlow serving service using Kubernetes service objects. Define a service of type load balancer or node port to provide external access to the TensorFlow serving endpoints. Next, load and serve TensorFlow models. Use TensorFlow serving configuration option to specify the model path and version to serve. Configure TensorFlow serving to load models from storage, example Google Cloud Storage, Amazon S3, and serve them over HTTP REST or gRPC endpoints. Next is scale and manage TensorFlow serving instances. Use Kubernetes features such as horizontal pod autoscaling (HPA) and cluster autoscaler to automatically scale TensorFlow serving instances based on resource utilization and incoming workload. Monitor TensorFlow serving pods and services using Kubernetes monitoring tools and dashboards. Scaling TensorFlow with TensorFlow serving and Kubernetes enables efficient deployment and serving of machine learning models in production environments. By containerizing TensorFlow models, deploying them as scalable services on Kubernetes clusters and leveraging TensorFlow's serving features for model serving and versioning, developers can build robust and scalable machine learning pipelines that handle varying levels of workload and ensure high availability. Understanding the key concepts and steps involved in scaling TensorFlow with TensorFlow serving and Kubernetes is essential for effectively deploying and managing machine learning models at scale in modern distributed systems. TensorFlow Extended. TFX. Let's go over the introduction to TensorFlow Extended, TFX. TFX is an end-to-end platform for deploying production machine learning pipelines at scale. It provides a comprehensive set of tools and libraries for building, training, validating, and deploying machine learning models in production environments. TFX enables developers to create robust and scalable machine learning pipelines that automate the entire machine learning workflow, from data ingestion and pre-processing to model deployment and monitoring. Let's dive deeper into the key components and features of TFX. The key components of TFX consists of several components that work together to create and deploy machine learning pipelines. First one is the TFX pipeline. The TFX pipeline defines the end-to-end workflow for training and deploying machine learning models. It consists of a series of components connected in a directed acyclic graph, or something called as DAG, where each component performs a specific task such as data validation, feature engineering, model training, evaluation, and deployment. TFX components. TFX provides a set of pre-built components for common machine learning tasks, including example gen, component for ingesting and pre-processing training data from various sources, example CSV files, BigQuery tables; statistics gen, component for computing descriptive statistics and data schema from training data; schema gen, component for inferring a schema from training data and detecting anomalies and inconsistencies; example validator, component for detecting anomalies and inconsistencies in training data based on the inferred schema; transform, component for performing feature engineering and data pre-processing user TensorFlow transform; trainer, component for training machine learning models using TensorFlow; evaluator, component for evaluating trained models and computing evaluation metrics; pusher, component for deploying trained models to production serving infrastructure. TFX orchestration. TFX provides orchestration tools for managing and executing machine learning pipelines. It supports various orchestration frameworks including Apache Airflow, Apache Beam, and Kubeflow pipelines, allowing developers to choose the most suitable orchestration platform for their deployment environment. TFX metadata store. TFX uses a metadata store to store and manage metadata related to pipeline execution, including pipeline run, component artifacts, and model lineage. The metadata store enables lineage tracking, versioning, and reproducibility of machine learning experiments. Let's look at features of TFX. TFX offers several features that make it a powerful platform for deploying production machine learning pipelines. End-to-end automation. TFX automates the entire machine learning workflow from data ingestion and pre-processing to model training, evaluation, and deployment. This enables developers to focus on building and refining machine learning models rather than managing infrastructure and workflows. Scalability and robustness. TFX is designed for scalability and robustness, allowing developers to build and deploy machine learning pipelines that handle large-scale datasets, complex feature engineering tasks, and distributed training scenarios. Customizability and extensibility. TFX provides a modular and extensible architecture that allows developers to customize and extend pipeline components to meet the specific requirements of their machine learning tasks. Developers can integrate custom pre-processing logic, feature engineering transformations, and model architectures into TFX pipeline seamlessly. Monitoring and governance. TFX includes tools for monitoring and governance, enabling developers to track pipeline execution, monitor model performance, and ensure compliance with regulatory requirements. This includes features such as modeling versioning, lineage tracking, and model monitoring. Next is deployment and integration. TFX pipelines can be deployed and integrated into various production environments, including on-premises data centers, cloud platforms, example Google Cloud Platform, Amazon Web Services, and Kubernetes clusters. TFX provides integration with TensorFlow serving for deploying trained models to production serving infrastructure and with Kubeflow for deploying pipelines on Kubernetes clusters. TensorFlow Extended is a powerful platform for building, training, and deploying production machine learning pipelines at scale. By providing a comprehensive set of tools and libraries for automating the entire machine learning workflow, TFX enables developers to create robust and scalable machine learning pipelines that handle large-scale datasets, complex feature engineering tasks, and distributed training scenarios. Understanding the key components and features of TFX is essential for effectively deploying and managing machine learning pipelines in production environment and realizing the full potential of machine learning for real-world applications. Building end-to-end ML pipelines with TFX. Building end-to-end machine learning ML pipelines with TensorFlow Extended involves orchestrating various components and stages of the ML workflow, from data ingestion and pre-processing to model training, evaluation, and deployment. TFX provides a comprehensive set of tools and libraries for building, validating, and deploying production ML pipelines efficiently. Let's dive deeper into the key steps and components involved in building end-to-end ML pipelines with TFX. The first step out of 7 steps that are there is define the ML pipeline. The first step in building an end-to-end ML pipeline with TFX is to define the pipeline structure and stages. This includes specifying the sequence of components and tasks to be executed, as well as the data sources, input features, and output targets. Next, data ingestion and pre-processing. TFX provides components for ingesting and pre-processing trained data, including example gen for ingesting data from various sources, example CSV files, BigQuery tables, and transform for performing feature engineering and data pre-processing user TensorFlow transform. Third step, data validation and schema inference. TFX includes components for data validation and schema inference, such as statistics gen for computing descriptive statistics from training data, schema gen for inferring a schema from training data, and example validator for detecting anomalies and inconsistencies in training data based on the inferred schema. Fourth, model training and evaluation. TFX provides components for model training and evaluation, including trainer for training machine learning models using TensorFlow and evaluator for evaluating trained models and computing evaluation metrics. Developers can define custom model architecture and training configurations using TensorFlow's API. Fifth, model deployment. Once a model has been trained and evaluated, TFX includes components for deploying the model to production serving infrastructure, such as Pusher for deploying trained model to TensorFlow serving or other serving platforms. Developers can specify deployment configurations and integration points with serving infrastructure. Monitoring and governance. TFX includes tools for monitoring and governance, allowing developers to track pipeline execution, monitor model performance, and ensure compliance with regulatory requirements. This includes features such as model versioning, lineage tracking, and model monitoring. Seventh, orchestration and execution. TFX pipelines can be orchestrated and executed using various orchestration platforms, including Apache Airflow, Apache Beam, and Kubeflow pipelines. These frameworks manage the execution of pipeline components, handle dependencies between tasks, and provide visibilities into pipeline execution. Building end-to-end ML pipelines with TensorFlow Extended involves orchestrating various components and stages of the ML workflow, from data ingestion and pre-processing to model training, evaluation, and deployment. By leveraging TFX's comprehensive set of tools and libraries,
developers can create robust and scalable ML pipelines that handle large-scale datasets, complex feature engineering tasks, and distributed training scenarios. Understanding the key steps and components involved in building end-to-end ML pipelines with TFX is essential for effectively deploying and managing ML workflows in production environments and realizing the full potential of machine learning for real-world applications. Model validation, transform, and serving with TFX. Building machine learning pipelines with TensorFlow Extended involves serving critical components including model validation, data transformation, and model serving. These components are essential for ensuring the quality and reliability of ML models in production environments. Let's deep dive into each of these components in the context of TFX. Model validation. Model validation is the process of assessing the performance and quality of trained ML models. In TFX, model validation is performed using the evaluator component, which evaluates trained models on held out validation data and computes evaluation metrics. Key aspects of model validation in TFX include evaluator component. The evaluator component evaluates trained models using evaluation metrics defined by the developer. It compares the predictions of the trained model against ground truth labels from validation data to assess model performance. Evaluation metrics. TFX supports various evaluation metrics for different types of ML tasks, including classification, regression, and ranking. Common evaluation metrics include accuracy, precision, recall, F1 score, mean square error, and area under the curve. Visualization and analysis. TFX provides tools for visualizing and analyzing evaluation results, including TensorBoard, dashboards, and custom visualization tools. Developers can use these tools to gain insight into model performance, identify area for improvement, and make informed decisions about model deployment. Data transformation. Data transformation is the process of pre-processing input data to prepare it for training and inference. In TFX, data transformation is performed using the transform component, which appeals feature engineering transformations to input data. Key aspects of data transformation in TFX include transform component. The transform component applies feature engineering transformations to input data such as normalization, scaling, one-hot encoding, and feature crossing. It uses TensorFlow Transform (TFT) to define and apply these transformations in a scalable and efficient manner. Schema inference. The transform component infers a schema from the input data and uses it to guide feature engineering transformations. The schema defines the expected data types, shapes, and ranges of input features, ensuring consistency and compatibility between training and serving data. Custom transformations. TFX allows developers to define custom feature engineering transformations using TensorFlow's APIs. This enables developers to implement domain-specific pre-processing logic and incorporate business roles into the data transformation process. Model serving. Model serving is the process of deploying trained ML models to production serving infrastructure for making predictions on new data. In TFX, model serving is facilitated by the pusher component, which deploys trained models to serving platforms such as TensorFlow serving. Key aspects of model serving in TFX include the pusher component. The pusher component deploys trained models to production serving infrastructure such as TensorFlow serving, Kubernetes, or cloud-based serving platforms. It converts trained models into a format compatible with the serving platform and manages the deployment process. Model versioning. TFX supports model versioning, allowing developers to deploy multiple versions of the model concurrently and switch between them seamlessly. This enables A/B testing, gradual rollouts, and model updates without downtime. Monitoring and management. TFX provides tools for monitoring and managing deployment
models, including integration with monitoring platforms, logging frameworks, and alerting systems. This enables developers to track model performance, monitor serving latency, and detect anomalies in real time. Model validation, data transformation, and model serving are critical components of ML pipelines in production environments. In TFX, these components are orchestrated and executed as part of end-to-end ML pipelines, enabling developers to build robust, scalable, and reliable ML systems. By leveraging TFX's tools and libraries for model validation, data transformation, and model serving, developers can ensure the quality and reliability of ML models throughout the entire lifecycle, from training and evaluation to deployment and monitoring. Understanding the key aspects and capabilities of model validation, data transformation, and model serving in TFX is essential for effectively building and deploying ML pipelines in production environments. Practical applications and projects is what we're going to look in this particular section. So there's some real world applications that I want to talk about, and next we'll look at some hands-on projects. So let's start with the real world application. And for real world applications, we're going to start with image classification first. Real world applications of image classification span various industries and use cases, leveraging machine learning techniques to analyze and interpret visual data. Image classification involves categorizing images into predefined classes or labels based on their visual content. This capability finds application in fields such as healthcare, automotive, retail, agriculture, security, and more. Let's dive deeper into some real-world applications of image classification with a focus on different industries. We'll start with healthcare. Now, healthcare has two of them that I want to discuss about. First one is medical imaging diagnosis. Image classification models are used to analyze medical images such as X-rays, MRI scans, and CT scans to assist healthcare professionals in diagnosing diseases and conditions. For example, detecting abnormalities in lung X-rays for early diagnosis of pneumonia, or identifying cancerous tumors in mammograms for oncology diagnosis. Second one is the pathology analysis. Image classification is applied in pathology to classify histopathology slides and microscope images of tissue samples. This helps pathologists identify and classify different types of cells, tissues, and abnormalities, aiding in the diagnosis and treatment of diseases such as cancer. The second industry that we want to look at is automotive, and here we'll discuss two different ones. One is autonomous driving, and second one is driving monitoring systems. In autonomous driving, image classification plays a crucial role in autonomous vehicles for object detection and recognition, lane detection, traffic sign recognition, pedestrian detection, and obstacle avoidance. Deep learning models analyze camera images and sensor data to interpret the surrounding environment and make real-time driving decisions. For driving monitoring systems, image classification models are used in driver monitoring systems to detect and classify driver actions and behaviors such as drowsiness, distraction, fatigue, and hand gestures. This enhances vehicle safety by alerting drivers to potential risk and improving driver assistance systems. The third industry is retail. In retail, product recognition. Image classification is employed in retail for product recognition and visual search applications. Retailers use ML models to automatically classify and categorize products based on their images, enabling features like product recommendation, inventory management, and visual search in e-commerce platforms. Customer behavior analysis. Image classification models analyze customer behavior and demographics based on surveillance cameras footage in retail stores. This helps retailers understand customer preferences, foot traffic patterns, and shopping behaviors to optimize store layouts, product placements, and marketing strategies. Next industry is agriculture. First one in agriculture is crop monitoring. Image classification is used in precision agriculture to monitor crops and detect plant diseases, pests, and nutrient deficiencies. Remote sensing techniques and drone imagery are employed to capture aerial images of fields, which are then analyzed by ML models to provide insights for crop management and yield optimization. Weed detection. Image classification models identify and classify weeds in agriculture fields to enable targeted weed control and herbicide application. By distinguishing between crops and weeds in images, farmers can implement precision spraying techniques to reduce herbicide usage and minimize environmental impact. The next and the last industry that we'll look at is security and surveillance. First one is facial recognition. Image classification is utilized in security systems for facial recognition and biometric authentication. ML models analyze facial features and patterns to identify individuals from images and video footage, enabling applications such as access control, identity verification, and surveillance. Second, object detection. Image classification models detect and classify objects of interest in surveillance footage, such as people, vehicles, and suspicious activities. This helps enhance security monitoring and threat detection in public spaces, airports, transportation hubs, and critical infrastructure. Image classification has a wide range of real-world applications across various industries, enabling automated analysis and interpretation of visual data. By leveraging machine learning techniques and deep learning models, organizations can extract valuable insights from images, improve decision-making processes, and enhance operational efficiency in diverse domains. Understanding the specific requirements and challenges of image classification tasks in different industries is crucial for developing effective and impactful solutions that address real-world needs. Natural language processing. Real-world applications of natural language processing cover a broad spectrum of industries and use cases, leveraging machine learning and deep learning techniques to analyze and understand human language. NLP facilitates tasks such as text classification, sentiment analysis, machine translation, named entity recognition, question answering, and more. Let's dive deeper into some real-world application of NLP with a focus on different industries. Start with healthcare again. First one is clinical document analysis. NLP is used in healthcare for analyzing clinical notes, medical records, and patient documents. It helps healthcare providers extract relevant information such as patient demographics, medical conditions, medications, and treatment plans to support clinical decision-making, patient care, and research. Next is drug discovery. NLP techniques are applied in pharmaceutical research for analyzing scientific literature, research papers, and clinical trials data. It aids in identifying potential drug candidates, understanding drug interactions, and extracting biomedical knowledge from vast amounts of textual information. Let's look at finance. First one is sentiment analysis. NLP is employed in financial markets for sentiment analysis of news articles, social media posts, and analyst report. It helps investors and financial institutions gauge market sentiment, assess market trends, and make informed investment decisions based on public sentiments towards stocks, commodities, and financial assets. Next is fraud detection. NLP techniques are used in banking and finance for detecting fraudulent activities such as phishing emails, fraudulent transactions, and identity theft. NLP models analyze textual data from customer communications, transaction logs, and financial reports to identify suspicious patterns and anomalies indicative of fraudulent behavior. Next industry is customer service, chatbots and virtual assistants. NLP powers chatbots and virtual assistants deployed in customer service applications such as an online support chatbot, virtual agents on websites, and voice assistants in call centers. These AI-driven systems understand natural language queries, respond to customer inquiries, and provide personalized assistance to improve customer satisfaction and streamline support operations. Sentiment analysis.
NLP is used in customer feedback analysis to analyze customer reviews, survey responses, and social media comments. It helps businesses track customer sentiment, identify issues, and gather feedback for product improvement and service optimization. Next industry, e-commerce. Product recommendations. NLP techniques are employed in e-commerce platform for product recommendation systems. By analyzing user search queries, browsing history, and purchase behavior, NLP models recommend relevant products to users, personalize product suggestions, and enhance the shopping experience. Product description analysis. NLP is used to analyze product descriptions, reviews, and specifications to extract product attributes, features, and sentiments. It helps e-commerce retailers understand customer preferences, optimize product listings, and tailor marketing campaigns based on consumer insights. Legal and compliance. Contract analysis. NLP is applied in legal and compliance domains for contract analysis and review. NLP models extract key terms, clauses, and legal entities from legal documents, contracts, and regulatory filings, facilitating contract management, due diligence, and compliance monitoring. Compliance monitoring. NLP techniques are used to monitor regulatory compliance by analyzing regulatory text, laws, and policies. NLP models help organizations stay updated on legal requirements, identify compliance risk, and ensure adherence to regulatory standards in areas such as data privacy, financial regulations, and healthcare laws. Natural language processing has a wide range of real-world applications across various industries, enabling organizations to analyze, interpret, and extract valuable insights from textual data. By leveraging NLP techniques and technologies, businesses can automate tasks, improve decision-making processes, enhance customer experiences, and gain competitive advantages in today's data-driven world. Understanding the specific requirement and challenges of NLP tasks in different industries is crucial for developing effective and impactful solutions that addresses real-world needs. Recommender systems. Real-world applications on recommender systems are pervasive across various industries, leveraging machine learning algorithms to provide personalized recommendations to users. Recommender systems analyze user preferences, behaviors, and historical interactions to suggest relevant items, products, or content, thereby enhancing user experience, increasing engagement, and driving business revenue. Let's dive deeper into some real-world applications of recommender systems with a focus on different industries. E-commerce. Product recommendations. Recommender systems are extensively used in e-commerce platforms to suggest products to users based on their browsing history, purchase behavior, and preferences. By analyzing users' interactions with products, recommender systems personalize product recommendation, cross-sell and upsell retail items, and improve conversion rates and sales revenue. Personalized shopping experience. Recommender systems enhance the shopping experience by providing personalized recommendations, curated collections, and tailored promotions to individual users. By understanding user preferences and shopping patterns, e-commerce retailers can deliver relevant and timely recommendations that match user interest and preferences. Streaming media industry. Content recommendations. Recommender systems power content discovery and recommendation engines in streaming media platforms such as Netflix, Amazon Prime Video, and Spotify. By analyzing users' viewing or listening history, preferences, and ratings, recommender systems suggest movies, TV shows, songs, playlists, and podcasts that match user taste, interest, and mood. Personalized playlist. Streaming media platforms use recommender systems to generate personalized playlists and curated content collection for users. By understanding user preferences, music genres, and listening habits, recommender systems create custom playlists, radio stations, and discovery channels
that cater to individual taste and preferences. Social media industry. Friend recommendations. Social media platforms employ recommender systems to suggest friends, connections, and followers to users based on mutual interests, social connections, and network activities. By analyzing user profiles, interactions, and social groups, recommender systems identify potential friends and connections that users may know or share common interests with. Content sharing. Recommender systems facilitate content sharing and discovery on social media platforms by recommending articles, posts, videos, and photos that users may find interesting or relevant. By analyzing user engagement, content preferences, and social interactions, recommender systems surface trending topics, viral content, and recommended posts in user feeds. Travel and hospitality industry. Hotel and travel recommendations. Recommender system assists travelers in finding hotels, accommodations, and travel destinations that match their preferences, budget, and travel requirements. By analyzing user search queries, booking history, and travel preferences, recommender systems suggest personalized travel packages, flight options, and hotel recommendations. Activity and experience recommendations. Recommender systems curate personalized activity recommendations and experiences for travelers based on their interests, hobby, and travel preferences. By understanding user preferences for outdoor activities, sightseeing, dining, and entertainment, recommender systems suggest personalized itineraries, tours, and local experiences. Online education industry. Course recommendations. Recommender systems help learners discover relevant courses, tutorials, and learning resources on online education platforms such as Coursera, Udemy, and Khan Academy. By analyzing learner profiles, learning objectives, and past course interactions, recommender systems suggest personalized course recommendations, learning paths, and skill development programs. Learning content personalization. Recommender systems personalize learning content and course material for individual learners based on their proficiency level, learning style, and subject preferences. By adapting learning content, quizzes, and assessments to match learner preferences and skill levels, recommender systems enhance learning outcomes and engagement. Recommender systems have become integral components of digital platforms and services across various industries, providing personalized recommendations to users, enhancing user experience, and driving business growth. By leveraging machine learning algorithms and data-driven approaches, organizations can analyze user behaviors, preferences, and interactions to deliver relevant and timely recommendations that meet individual user needs and preferences. Understanding the specific requirements and challenges of a recommendation system in different industries is crucial for developing effective and impactful recommendation engines that deliver value to users and businesses alike. Object detection. Real-world applications of object detection involve detecting and localizing objects within images or video frames, enabling various use cases across industries. Object detection systems utilize machine learning algorithms, particularly deep learning models such as convolutional neural networks (CNNs), to identify and classify objects of interest within visual data. Let's dive deeper into some real-world applications of object detection with a focus on different industries, starting with first, autonomous vehicles. Pedestrian detection. Object detection is crucial for detecting pedestrians, cyclists, and other vehicles in the vicinity of autonomous vehicles. It helps in identifying potential obstacles and avoiding collisions, ensuring the safety of passengers and pedestrians on the road. Traffic sign recognition. Object detection systems recognize and interpret traffic signs, signals, and road markings to provide situational awareness to autonomous vehicles. This includes detecting stop signs, traffic lights, speed limit signs, and lane markings, allowing vehicles to adhere to traffic regulations and navigate safely. Surveillance and security industry. Intrusion detection. Object detection is employed in surveillance system for detecting intruders, unauthorized personnel, or suspicious activities in restricted areas. It helps security personnel identify potential threats and respond promptly to security breaches or perimeter breaches. Object tracking. Object detection systems track the movement and trajectory of objects within a surveillance scene, enabling real-time monitoring and analysis of moving targets. This includes tracking individuals, vehicles, or objects of interest across multiple frames of video footage. Next industry is retail and inventory management. Customer tracking. Object detection systems track customer movements and behavior within retail stores, analyzing foot traffic patterns, dwell times, and customer interaction with products. This data helps retailers optimize store layouts, product placements, and marketing strategies to enhance the shopping experience. Shelf monitoring. Object detection is used in retail environment to monitor product shelves and inventory levels. It helps retailers detect out-of-stock items, identify misplaced products, and optimize replenishment procedures to ensure product availability and reduce stockouts. Industrial automation. Defect detection. Object detection systems inspect manufacturing components and products for defects, anomalies, or quality issues. This includes detecting surface defects, cracks, scratches, or deviations from specified dimensions in manufactured parts or assemblies. Object sorting and handling. Object detection is employed in robotic systems for sorting, picking, and handling objects in industrial environment. It helps robots identify and grasp objects with precision, enabling automated assembly, packaging, and material handling tasks. Healthcare industry. Medical imaging analysis. Object detection is used in medical imaging for detecting and localizing abnormalities, lesions, or anatomical structures within medical images. This includes detecting tumors, nodules, fractures, or anomalies in X-rays, MRI scans, CT scans, and ultrasound images. Surgical assistance. Object detection system assists surgeons in surgical procedures by identifying and localizing surgical instruments, anatomical landmarks, and critical structures within the surgical field. This helps improve surgical precision, reduce errors, and enhance patient outcomes. Object detection has a wide range of real-world applications across various industries, enabling automated analysis and interpretation of visual data for diverse use cases. By leveraging machine learning algorithms and deep learning models, organizations can develop object detection systems that enhance safety, security, efficiency, and productivity in various domains. Understanding the specific requirements and challenges of object detection tasks in different industries is crucial for developing effective and impactful solutions that addresses real-world needs. Welcome to the section for hands-on projects. Here we will build 4 different projects and then go through the code each and every time, and then see how we can make it better. The first one that we have is building a sentiment analysis model. Certainly below is a step-by-step guide for building a sentiment analysis model using TensorFlow, focusing on neural network architecture. Step 1 is data preparation. So with data preparation, the first thing that you have to do is data collection. Obtain a data set of text documents with sentiment labels positive, negative, neutral. You can use public data sets like IMDb, movie reviews, or Twitter sentiment analysis dataset. Next is data preprocessing. Preprocess the text data by tokenizing, padding sequences, and encoding labels. For example, tokenize the text into word or tokens. Convert words to integers using a tokenizer. Pad sequences to ensure uniform length. Step 2 is building the neural network model. Define model architecture. Build a neural network model for sentiment analysis using TensorFlow's Keras API. You can start with a simple architecture like a bidirectional LSTM followed by a dense layer. Compile the model by specifying the loss function, optimizer, and evaluation metrics. Next step is training the model. Split the data set into training and testing sets. Next, train the model. Train the sentiment analysis model on the training data. Use techniques like early stopping to prevent overfitting. Next step is model evaluation. In this, we do evaluate the performance. Evaluate the model's performance on the testing data using metrics like accuracy, precision, recall, and F1 score. Next step is model deployment. Save the trained model, weights, and architecture for future use, and then deploy the model. Deploy the sentiment analysis model using a suitable deployment strategy such as deployment as REST APIs using TensorFlow serving or Flask. Sixth step, or the last step, is continuous improvement. Fine-tuning the model architecture and hyperparameters based on performance metrics and user feedback. Update the model. Periodically update the sentiment analysis model with new data and retrain it to adapt changing trends and patterns. Here is an example code. Let's go over this to see how we have implemented the sentiment analysis model. So first, we need to import TensorFlow. Then we have to import tokenizer from TensorFlow Keras pre-processing text. Next, import pad sequences from Keras pre-processing sequence. The first step for data preparation. Assuming text contains list of text documents and labels contain corresponding sentiment labels. We're going to tokenize and pad sequences. Use a tokenizer function. Pass num words equal to number of words equal to 10,000 and OOV token is OOV. Tokenizer dot fit on text function and pass the text to that. Next, we'll call the text to sequences function available in the tokenizer and pass text to it. Next, we'll call the pad sequence and pass the sequences max length of 100, padding of post, and truncating with post, and pass and assign it to padded sequences. This is data preparation. Now next is building the neural network model, which we have done before. Now we have to implement it here with calling the sequential function of the Keras and pass and call the embedding function, pass the values. Next is bidirectional, pass the layers LSTM that we are using. Next, the dense layers, we call the dense function, pass the 64 and activation value, and the next one pass 1 and activation of sigmoid. So next, we'll compile the model. So what we're going to do is we call the compile function, pass the optimizer as Adam, loss as binary cross entropy, and metrics as accuracy. Step 3, let's train the model. You pass xtrain, xtest, ytrain, ytest. These are the values that you'll get, tuple that you'll get from training test split function. You pass the padded sequences, labels, test size, and random state to it. Next, we're going to fit the model by calling model.fit function and pass it to give it to history. Xtrain, ytrain is what we pass, epochs of 10, validation data, xtest and ytest that we got, and then batch size of 32. Next step is model evaluation, where we call the evaluate function, and we pass the xtest and ytest to it and get loss and accuracy out. You can print those things out. Model deployment, you can save the model as I mentioned and then deploy it wherever you want using using either TensorFlow serving or anything else that you prefer. Step 6 is continuous improvement. So based on the feedback, you will fine tune the model, update the data, and retrain the periodically at this particular point. This example demonstrates how to build a sentiment analysis model using TensorFlow's Keras API. You can further enhance the model's performance by experimenting with different architectures, hyperparameters, and pre-processing techniques. Additionally, consider incorporating techniques like word embeddings, example word-to-vec or GLOV or glove, and attention mechanisms to improve the model's ability to capture semantic meaning and context in text data. In this particular video, we're going to create an image recognition system. Here's a step-by-step guide for creating an image recognition system using TensorFlow. First step
is data collection and preparation. So dataset selection, choose a dataset suitable for image recognition task. Popular data set include Cipher 10, Cipher 100, MNIST, ImageNet, etc. We have used MNIST before in one of the examples, but we'll see more. Data preprocessing. Pre-process the images by resizing them to a uniform size, normalizing pixel values, and converting them to arrays. TensorFlow provides tools like Image Data Generator for pre-processing. Step 2. Building the convolutional neural network or CNN model. Model architecture. Design a CNN architecture suitable for image recognition. You can start with a simple architecture like LeNet or use more complex architectures like ResNet, Inception, etc. Model definitions. Define the CNN model using TensorFlow's Keras API. Specify the number of convolutional layers, pooling layers, fully connected layers, and output layers. Step 3 is model training. First one is data augmentation in there. Augment the training data using techniques like rotation, scaling, shearing, etc. to increase dataset diversity and improve model generalization. Next, compile the model. Compile the CNN model by specifying the loss function, optimizer, and evaluation metrics. Next, training. Train the CNN model on the training dataset using TensorFlow's fit function. Monitor training progress using callbacks like model checkpoint and early stopping. And step 4 is model evaluation. Validation. Evaluate the trained model performance on the validation dataset using metrics like accuracy, precision, recall, and F1 score. Fine-tuning. Fine-tune the model architecture and hyperparameters based on validation performance to optimize model performance. Step 5 is model deployment. Save the model, save the trained model, weights, and architecture using TensorFlow's save function for future use. Deployment. Deploy the image recognition model using a suitable deployment strategy such as deploying as a REST API using TensorFlow serving or Flask. Step 6 is continuous improvement. Monitoring and maintenance. Monitor the deployed model performance in real-world scenarios and update it periodically with new data or fine-tuning to maintain accuracy and adapt to changes. Let's look at an example of how you would implement this if you do it in Python. So first, import TensorFlow, then import layers and models from Keras. Now let's build the CNN model. So first, you're going to take the models, you can create the sequence, call the sequential function and pass the conv_td and pass the parameters to it. You can then do the max pooling 2d, then again conv_2d and then max pooling 2d. Next again conv_2d, pass the parameters and then flatten it. And then to add some dense layers, call the dense function and pass the parameters. Again call the dense functions with the parameters using softmax as the activation. So this will build your CNN model. Next is model training. You can first compile using the optimizer, loss function, and metrics. Here we're using Adam as optimizer, sparse categorical cross entropy as the loss function, and for metrics we're using accuracy. Next, fit the model by calling the fit function and pass it to history, where the arguments are trained images, trained labels, epochs of 10, and validation data set is test images and test labels. Step 4 is model evaluation. Now we can get the tuple for test loss and test accuracy by calling the evaluate function and pass test images and test labels to it. You'll get the test. You can print out the values that you get. You can next save the model and deploy it using serving or Flask. Continuous improvement step is where you monitor the performance, fine-tune the model, and update with new data periodically. So this is the entire steps for actually creating an image recognition system. This example demonstrates how to create an image recognition system using TensorFlow. You can customize the model architecture, pre-processing techniques, and deployment strategies based on your specific requirements and dataset characteristics. You can look at some of the previous videos where we have done this. Additionally, consider exploring advanced techniques like transfer learning and ensemble methods to further improve model performance. Next hands-on is developing a time series prediction model.
Below is a step-by-step guide for developing a time series prediction model using TensorFlow. Step 1 is data collection and preparation. First, for that, you do data selection, where you choose a time series dataset suitable for prediction task. Examples include financial data, weather data, stock prices, etc. Next is data processing. Pre-process the time series data by handling missing values, scaling the data, and splitting it into training and testing sets. Step 2 is building the recurrent neural network model, RNN. Model architecture. So design an RNN architecture suitable for time series prediction tasks. Common choices include long short-term memory, LSTM, and gated recurrent unit, GRU networks. Model definition. Define the RNN model using TensorFlow Keras API. Specify the number of LSTM or GRU layers, hidden units, activation functions, etc. Step 3 is model training. So first you do data preparation. Prepare the time series data in sequence or windows suitable for training the RNN model. Use techniques like sliding windows or time series generators. Next, compile the model. Compile the RNN model by specifying the loss function, optimizer, and evaluation metrics. Next, do the training. Train the RNN model on the training dataset using TensorFlow's fit function. Monitor training progress using callbacks like model checkpoint and early stopping. Next step is model evaluation. First, validation. Evaluate the trained model's performance on the validation dataset using metrics like mean squared error, MSE, mean absolute error, MAE, etc. Next, to fine-tuning. Fine-tuning the model architecture and hyperparameters based on validation performance to optimize model performance. Next step is model deployment. Save the model, save the trained model, weights and architecture using TensorFlow's save function for future use. Next, to deployment. Deploy the time series prediction model using a suitable deployment strategy, such as deploying as a REST API using TensorFlow serving or Flask. Step 6 is continuous improvement. Monitoring and maintenance. Monitor the deployed model's performance in real-world scenarios and update it periodically with new data or fine-tuning to maintain accuracy and adapt to examples. Here is a code sample of how to do this. So first, import TensorFlow, then layers and models from TensorFlow Keras. How to build RNN model? You can call the sequential function and pass the layers function of LSTM, pass the parameters, then call the dense layers and pass the parameters. Next, you do model training by calling the compile function first, then fit, and then do the model evaluation. While doing model evaluation, you can call the evaluate function and pass the values of x test and y test to it, which will give you the test loss. Here you can print just to see the loss evaluation here. Next, do the model deployment. First, save it, and then you can deploy it using the Terraform serving or Flask. And once this model runs, you can do the continuous improvement as and when you monitor the performance, fine-tune the model, update with new data periodically. This example demonstrates how to develop a time series prediction model using TensorFlow's Keras API. You can customize the model architecture, pre-processing techniques, and deployment strategy based on your specific requirements and dataset characteristics. Additionally, consider exploring advanced techniques like attention mechanisms and ensembling methods to further improve model performance. This is my favorite hands-on example of implementing a chatbot. Everybody needs a chatbot. So building a chatbot involves natural language processing techniques and matching learning models. Below is a simplified step-by-step guide. Let's go over these steps one at a time. First one is data collection and pre-processing. In this, first we do is a data selection. Choose a data set suitable for training a chatbot. Common data sets include conversational data from chat logs, forums, or customer support interactions. Next, data pre-processing. Pre-process the text data by tokenizing, cleaning, and vectorizing it. Remove punctuation, special characters, and stop words. Convert text into numerical vectors using techniques like word embedding, example word to vec or glove. Step 2 is building the sequence to sequence model. First, model architecture. Design a sequence to sequence model for chatbot responses. The model typically consists of an encoder-decoder architecture with recurrent neural networks RNNs or transformer layers. Model definition. Define the sequence to sequence model architecture using TensorFlow's Keras API. Implement encoder and decoder components with appropriate layers like LSTM, GRU, or attention mechanisms. Step 3 is model training. Data preparation. Prepare the conversational data to input-output pairs suitable for training the sequence to sequence model. Compile the model. Compile the sequence to sequence model by specifying the loss function, optimizer, and evaluation metrics. Training. Train the sequence to sequence model on the training dataset using TensorFlow's fit function. Monitor training progress and performance. Next step is model evaluation. Validation. Evaluate the trained model's performance on a validation dataset using metrics like BLEU score, perplexity, etc. Last step is chatbot interaction. User input. Accept user input or queries from the chat interface. Model interface. Process the user input through the trained sequence to sequence model to generate responses. Output. Display the generated response in user in a chat interface. Here is a code snippet of how to do this. So first, let's import TensorFlow. Next, we are importing input LSTM and dense layers from Keras layers. Then we are importing models from Keras models. Next, define the sequence to sequence model architecture. We'll create a variable called as latent dim and assign it value 256. Next is encoder inputs. We're going to call the input function and pass it shape of none and num encoder tokens. Next, we create an encoder variable, pass it LSTM with the latent dim that we created above, and return state equal to true. Next, we'll get the three different variables using the tuple function encoder. We get encoder output, state h, and state c by calling the encoder function and passing it the encoder inputs. Next, encoder states, we get it from the array of state h and state c. Next, decoder inputs. We get the input, again almost similar as the encoder where we call the input function, but instead of encoder we give the decoder tokens. Then decoder LSTM, we call the LSTM function and get the latent dim, return sequence equal to true and return state equal to true. Decoder outputs, comma underscore underscore, we don't need these, so that's why these are underscore underscore, equal to decoder LSTM, decoder inputs, and input state equal to encoder states. Now decoder dense is a dense layer we create here using the dense function by passing it the number of decoder tokens and activation equal to softmax. Decoder outputs, we call the decoder dense function and pass it the decoder output that we get. Then we call the model function and pass it the encoder inputs, decoder inputs in an array, and then the next parameter of decoder outputs. Then we compile the model by calling the compile function. We pass the optimizer as RMS prop and loss function of categorical cross entropy. Then we train the model by calling the fit function and pass it an array of encoder input data, decoder input data, and then pass the decoder target data. Next is the batch size and epochs and validation split. Now save the train model by calling the save. You can also deploy it here. And then finally implement chatbot interaction using the trained model by creating a chatbot response and get the input text in there and return the generated text. Inside this you can pre-process input text, you can do encode input text using the encoder model, generate response using the decoder model, and decode response token into text. This example demonstrates how to implement a simple chatbot using a sequence to sequence model architecture with TensorFlow's Keras API. You can further enhance the chatbot's performance by experimenting with different architectures, training strategies, and techniques like attention mechanisms. Additionally, consider integrating the chatbot with an external APIs or services for more advanced functionality. Welcome to part 6.
In this, we'll focus more on further learning and resources. We're going to go through a couple of topics. The first one is advanced topics and future directions. And in this advanced topics, we're going to first talk about generative adversarial networks, or GANs. Generative adversarial networks are a class of deep learning models introduced by Ian Goodfellow and his colleagues in 2014. GANs consist of two neural networks, the generator and the discriminator, which are trained simultaneously in a competitive manner. As you can see from the names, the generator learns to produce synthetic data samples that are indistinguishable from the real data, while the discriminator learns to differentiate between real and fake samples. So to go over some of the overview of GANs, GANs are composed of two neural networks, the generator and the discriminator. The generator generates synthetic data samples from random noise. The discriminator evaluates whether a given sample is real from the training data or fake generated by the generator. The generator and discriminator are trained simultaneously through adversarial training. That's why it's called generative adversarial networks. The architecture of GANs has the generator, which we already know, that takes random noise as input and generates synthetic data samples. The next one is the discriminator, takes real or fake data samples as input and predicts whether they are real or fake. The generator and discriminator are typically implemented using deep neural networks such as multi-layer perceptrons (MLPs) or convolutional neural networks (CNNs). For the training procedure, it's three steps. First is initialization, where you initialize the parameters of the generator and the discriminator networks. The next step is adversarial training, where the generator generates fake sample from random noise. The discriminator classifies both real and fake samples as real or fake. The generator is trained to produce samples that fool the discriminator, maximizing the probability of fake samples being classified as real. The discriminator is trained to correctly classify real and fake samples, minimizing the probability of misclassification. And the third step, optimization, is where you update the parameters of both networks using backpropagation and gradient descent based optimization algorithms. One of them is ADAM. The next we'll talk about is loss functions. Now for the generator loss, it measures how well the generator fools the discriminator. It is typically the negative of the discriminator loss on fake samples, whereas the discriminator loss measures how well the discriminator distinguishes between real and fake samples. It is the sum of the losses on real and fake samples. Next topic is about common variants of GANs. There are four of them. One is the deep convolutional GANs, which is DC GANs. GANs with convolutional neural networks in generator and discriminator, commonly used for image generation tasks. Next one is conditional GANs or CGANs. GANs conditioned on additional information such as class labels to generate samples with specific attributes. Next one is Wasserstein GANs or WGANs. GANs with the Wasserstein distance-based loss function, leading to more stable training and better sample quality. The last one is the cycle GANs, which is GANs used for unpaired image-to-image translation task, learning mapping between two domains without paired training data. The applications of GANs include image generation, where you generate realistic images of faces, objects, scenes, etc. You've probably seen some of those online these days. Image to image translation, translate image between different domains such as day to night, black and white to color, etc. Style transfer artistic styles between images, more like a signature of an artist. Data augmentation, where generate synthetic data samples to augment training data sets. Anomaly detection, detect anomalies in data by generating samples and identifying deviations from the training distribution. Generative adversarial networks have revolutionized the field of generative modeling and have applications in various domains, including computer vision, natural language processing, and healthcare. However, training GANs can be challenging due to instability and mode collapse issues. requiring careful design choices and training strategies to achieve good performance. Reinforcement learning with TensorFlow. Reinforcement learning (RL) is a type of machine learning paradigm where an agent learns to make decisions by interacting with an environment to maximize cumulative rewards. TensorFlow, being a powerful deep learning framework, provides tools and libraries for implementing RL algorithms and training agents to perform various tasks. Let's get into deep dive into RL with TensorFlow. So first, to understand the basics of reinforcement learning, what are the different aspects of it? First one is the agent, which is the learner or decision maker that interacts with the environment. The second, environment, is the external system or world with which the agent interacts. State, a representation of the current situation or configuration of the environment. Next is action, the decisions or choices made by the agent at each time step. Next is reward, the feedback signal from the environment indicating the goodness or desirability of the agent's actions. Next is policy, the strategy or rule used by the agent to select actions in different states. Next is value function, which estimates the expected cumulative reward of following a particular policy in a given state. The next thing that we learn is the algorithms, reinforcement learning algorithms. The first one is Q-learning, a model-free RL algorithm that learns action value functions, which are called Q values, through exploration and exploitation. Next one is Deep Q networks, which is DQN, an extensive of Q learning that uses deep neural networks to approximate Q values for high dimensional state spaces. Next we have policy gradient methods, directly learn the policy function to maximize expected rewards by gradient ascent. Next is actor critic methods, which combines elements of both value-based and policy-based methods with separate networks for actor policy and critic value function. Next is proximal policy optimizations, also called as PPO, a policy gradient algorithm that aims to find stable policy updates. These are different algorithms that we have. Next, we look at implementing reinforcement learning with TensorFlow. So the different steps are: first is define the environment. Implement the environment in which the agent will operate. This includes defining the state space, action space, reward function, and transition dynamics. Next is create the agent. Define the RL agent using TensorFlow. This involves designing the neural network architecture for the agent, including the policy network, value network, or any other required components. Next, we have to choose the RL algorithm. Select a suitable RL algorithm, whatever we saw above, based on the problem requirements and characteristics. TensorFlow provides implementation for various RL algorithms that we spoke about, such as like the DQN, PPO, SAC, which is also soft actor critic, etc. Next, we go into the training loop, where we implement the training loop where the agent interacts with the environment, collect experiences like state, action, reward tuples, and updates its parameters using backpropagation and optimization algorithms. The last step is evaluation, where you evaluate the trained agent's performance on unseen environment or test scenarios to assess its generalization and effectiveness. Next topic we look at is TensorFlow libraries for reinforcement learning. We have the TF agents, which is TensorFlow library for building and training RL agents, providing implementations of various RL algorithms, utilities, and environments. Next is OpenAI baselines, a set of high quality implementations of RL algorithm developed by OpenAI, which can be used with TensorFlow. So there's a lot of different libraries coming out, but these are the top two that people are using right now. Next, we have applications of reinforcement learning. Where is it used? So first one is the game playing, where RL has achieved remarkable success in playing games like Go, chess, and video games. Next is robotics, where RL is used to train robots to perform complex tasks like manipulation, locomotion, and navigation. Next is everybody's favorite, autonomous vehicles, where RL techniques are applied in developing autonomous vehicles for decision making and control. We have recommendation systems. RL can be used to personalize recommendations and optimize user engagement. Last is finance, where RL algorithms are employed in algorithm trading, portfolio management, and risk assessment. So if you are into trading stocks, don't do it, just use these algorithms. It will probably be better than what you are thinking. So reinforcement learning with TensorFlow offers a powerful framework for training agents to solve complex decision-making problems across various domains. By leveraging deep learning techniques and TensorFlow's extensive capabilities, developers can build and deploy RL systems for real-world applications with ease. However, RL requires careful tuning of hyperparameters. It has exploration strategies and reward function to achieve optimal performance. Quantum machine learning with TensorFlow Quantum. Quantum machine learning is an interdisciplinary field that combines principles from quantum physics and machine learning to solve computational tasks. TensorFlow Quantum, or something called as TFQ, is an open source library developed by Google that allows researchers and developers to build and train quantum machine learning models using TensorFlow. The first one, basics of quantum computing. We have qubits, or something that is called as quantum bits, are the fundamental units of quantum information, analogous to classical bits. Unlike classical bits, which can be either 0 or 1, qubits can exist in superposition states representing a combination of both 0 and 1 simultaneously. Quantum gates. Quantum gates are the basic building blocks for quantum circuits, similar to classical logical gates. They operate on qubits to perform operations such as rotations, flips, and entanglement. Next, we have quantum circuits. Quantum circuits are composed of a sequence of quantum gates applied to qubits, representing quantum algorithms. The last one is quantum measurement. Its measurement in quantum computing involves extracting classical information from quantum systems. It collapses the quantum state to a classical state. Let's go into quantum machine learning. Now, quantum data encoding is the first part here, which represents classical data into quantum states to leverage the computational advantages of quantum systems. Quantum variational algorithms, on the other hand, employ parameterized quantum circuits (PQC) to perform optimization tasks such as optimization, classification, regression, etc. The last one is quantum neural networks. Quantum neural networks are models that combine classical and quantum layers to perform learning tasks using techniques like quantum gates and parameterized circuits. Let's go into TensorFlow Quantum. Integrating with TensorFlow. So TFQ seamlessly integrates with TensorFlow, allowing users to combine classical and quantum operation within the same computational graph. The quantum circuits as tensors represent quantum circuits as TensorFlow tensors, enabling automatic differentiation and optimization using TensorFlow's gradient-based optimization algorithm. Hybrid classical quantum models. You can build hybrid models that combine classical and quantum components for performing machine learning tasks. We have access to quantum hardware. TFQ provides interfaces to access quantum processors from hardware providers like Google, Cirq, and IBM's Qiskit. The components of TensorFlow Quantum, there are three of them. The first one is circuit library. TFQ provides a library of predefined quantum circuits and gates for building quantum machine learning models. It provides quantum layers, which implement quantum layers such as quantum convolutional layers, quantum pooling layers, and quantum measurement layers for constructing quantum neural networks. Next, we have quantum kernels. They develop custom quantum kernels for performing quantum operations and transformations. The applications of TensorFlow Quantum are quantum generative models. These generate quantum data samples and distributions using variational quantum circuits. The next one is quantum optimization. It solves optimization problems using quantum algorithms and variational quantum eigensolvers. The next one is quantum chemistry. Simulate molecule. So it helps you simulate molecular structures and properties using quantum machine learning techniques. The last one is the quantum circuit learning, which trains quantum circuits to perform classifications, regressions, and other machine learning tasks. Now, if you want to get started with TensorFlow Quantum, you'll first have to install the TensorFlow Quantum and its dependencies. You then have to explore TFQ's tutorial. There's good tutorial and documentation for learning how to build and train these quantum machine learning models. And the last option is to experiment with these quantum circuits, the variational algorithms, and hybrid classical quantum models that we explained using TFQ's APIs and other tools. TensorFlow Quantum provides a powerful platform for researchers and developers to explore and experiment with quantum machine learning techniques, paving the way for integration of quantum computing into mainstream machine learning workflows. However, as quantum hardware is still in its early stages of development, practical application of quantum machine learning may require advancements in hardware technology and algorithms, and the fact that it's very expensive to play with it right now. Let's go to the second section of part 6, which is about resources and communities. So let's look at the TensorFlow documentation and tutorials. Now, while you're working on it, it's very important to get all this information, because everything that we cover here might not be available. Also, there's updates. So TensorFlow offers a wealth of documentation and tutorials to help users learn and master its various functionalities. Here's a deeper dive into TensorFlow documentation and tutorials, along with where you can find them online. So the TensorFlow documentation has official website, where the primary source of the documentation is the official TensorFlow website. Here you can find comprehensive documentation covering TensorFlow APIs, concepts, guides, and best practices. The next place that I would probably go is API documentation. TensorFlow API documentation provides detailed information about classes, functions, modules, and parameters within TensorFlow's Python API. You can navigate the API documentation from the TensorFlow website or directly from Python using the help function or by browsing the source code. The last one is the GitHub repository, which is my favorite, where Teraflow source code and documentation are hosted, and you can access the TensorFlow GitHub repository here to explore the documentation, contribute to the project, and access additional resources. For TensorFlow tutorials, if you want to learn more on it, the official tutorials are available with TensorFlow. TensorFlow offers a wide range of official tutorials covering various machine learning and deep learning topics. You can find these tutorials on the TensorFlow's tutorial page of the official website. They are organized by topic and difficulty level, making it easy for users to find tutorials relevant to their interest and expertise. Next is the GitHub repository. Again, the TensorFlow's GitHub repository contains a collection of tutorial notebooks and code samples. You can access these tutorials by browsing the TensorFlow/TensorFlow repository on GitHub and exploring the TensorFlow examples directory. Last one is the Google Colab. Many TensorFlow tutorials are available as interactive Google Colab notebooks, allowing users to run and experiment with code directly in their browsers. You can access these Colab notebooks from the official TensorFlow website or GitHub repository. For additional resources, you can go to TensorFlow blog. TensorFlow's official blog publishes articles, tutorials, case studies, and updates on TensorFlow related news, research, and developments. You can access the TensorFlow blog here to stay informed about the latest TensorFlow advancements and best practices. Next we have is the community contributions. TensorFlow has a vibrant community that contributes additional tutorials, guides, and resources covering niche topics and advanced techniques. You can find community contributed tutorials and resources on platforms like GitHub, Medium, personal blogs, and community forums. The last one is the online course and learning platforms. There are various online courses, learning platforms, and educational websites that offer tutorials, TensorFlow tutorials, and resources as part of their machine learning and deep learning curriculum. Examples include Coursera, Udacity, EDX, and others. The last topic is about the TensorFlow documentation updates. TensorFlow regularly updates its documentation to reflect changes in APIs, new features, and best practices. Users should refer to the latest version of the documentation to ensure they have access to the most up-to-date information. The current recording is done in January of 2024, so there might be updates to this particular version. Users can provide feedback, report issues, and contribute to improving TensorFlow documentation by submitting pull requests, raising GitHub issues, or participating in community discussions. In summary, TensorFlow documentation and tutorials are valuable resources for users looking to learn TensorFlow, explore its capabilities, and build machine learning models and applications. Whether you are a beginner or an experienced practitioner, you can find a wealth of information and resources online to help you leverage TensorFlow effectively for your projects and applications. TensorFlow's popularity has led to creation of numerous online courses and books dedicated to teaching users how to use TensorFlow effectively for machine learning and deep learning tasks. Here's a closer look at some popular TensorFlow online courses and books. The first courses that I probably would recommend is Coursera has TensorFlow in Practice Specialization. It's offered by Coursera, deeplearning.ai, and this specialization consists of 4 courses covering TensorFlow basics, data pipelines, CNNs, sequence models, and deployment. The next one is Udacity, which has Intro to TensorFlow for Deep Learning. This course provides an introduction to TensorFlow covering basics, neural networks, CNNs, and NLP using TensorFlow. Next, EDX has Deep Learning with TensorFlow. This course covers deep learning concepts and TensorFlow implementations for building neural networks. There's also DataCamp, which has Introduction to TensorFlow in Python. This course introduces TensorFlow basics and covers building neural networks for various tasks. Some of the books that cover TensorFlow pretty well are Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. This book provides a comprehensive guide to machine learning with practical examples using TensorFlow and Keras. Next book is Deep Learning with Python, authored by the creator of Keras. This book covers deep learning fundamentals and practical implementation using TensorFlow and Keras. The next book is TensorFlow 2.0 in Action. This book offers a hands-on approach to learning TensorFlow 2.0, covering neural networks, NLP, computer vision, and more. The last book that I could recommend is TensorFlow for Deep Learning, from linear regression to reinforcement learning. This book covers TensorFlow basics to advanced topics like reinforcement learning with practical examples and case studies. Additional resources that you can look for are official TensorFlow documentation and tutorial. This official website provides extensive documentation, tutorials, and guides for learning TensorFlow from scratch. Next one is community forums and discussion groups. TensorFlow has active community forums and discussion groups where users can ask questions, share knowledge, and seek help from fellow practitioners. Last one, my favorite, is the GitHub repositories and projects. Exploring TensorFlow projects on GitHub can provide practical examples, code snippets, and real-world applications of TensorFlow in various domains. Whether you prefer self-paced online courses, books, or a combination of both, there are plenty of resources available to help you learn TensorFlow effectively and apply it to your machine learning and deep learning projects. The TensorFlow community is a vibrant and active ecosystem of developers, researchers, students, and enthusiasts who come together to share knowledge, collaborate on projects, and support each other in learning and using TensorFlow. Here's an overview of TensorFlow community and forums. The TensorFlow forum is the official TensorFlow forum is dedicated platform for users to ask questions, share insights, and engage in discussions related to TensorFlow and machine learning. It's monitored by TensorFlow team members and experienced community members. TensorFlow's GitHub repository serves as a central hub for contributing code, reporting issues, and discussing development topics related to TensorFlow and its ecosystem projects. Users can participate in discussions, submit pull requests, and contribute to open source projects.
The TensorFlow LinkedIn group provides a platform for professionals to connect, share resources, and discuss TensorFlow related topics. It's a great place for networking and staying updated on TensorFlow news and development. TensorFlow meetups are community organized events where TensorFlow enthusiasts gather to share knowledge, showcase projects, and network with peers. These meetups are held worldwide and cover a wide range of topics related to TensorFlow and machine learning. What are the benefits of participating in TensorFlow community? First is knowledge sharing. The TensorFlow community provides a platform for users to share their knowledge, experiences, and best practices in using TensorFlow for various machine learning tasks. The support and collaboration. Community members offer support and guidance to fellow users by answering questions, troubleshooting issues, and collaborating on projects. For networking, engaging with TensorFlow community allows users to connect with like-minded individuals, form professional relationships, and collaborate on research projects and initiatives. Learning opportunities. Community forums, meetups, and events offer valuable learning opportunities through tutorials, workshops, presentations, and discussions on TensorFlow related topics. Contributing to open source. Users can contribute to the TensorFlow ecosystem by submitting bug fixes, enhancements, documentation improvements, and new features to TensorFlow's GitHub repository. What are the tips for engaging in TensorFlow community? You have to be respectful, treat your fellow community members with respect, kindness, and professionalism in all interactions. Ask questions. Don't hesitate to ask questions on the forum or in other community platforms if you need help or clarification on TensorFlow related topics. Contribute back. Share your knowledge, expertise, and contributions with the community by answering questions, providing feedback, and contributing to open source projects. Stay updated. Keep up to date with TensorFlow news, announcements, events, and releases by following official channels, blogs, and social media accounts. How to contribute to the TensorFlow community? You can contribute by code. Contribute to TensorFlow's open source projects by submitting pull requests, addressing issues, and participating in code reviews. You can write tutorials and guides. Something that I'm doing right now is share your TensorFlow knowledge and expertise by writing tutorials, guides, and blog posts for the community. You can organize events. Organize TensorFlow meetups, workshops, or hackathons in your local area to bring together TensorFlow enthusiasts and foster collaboration and learning. By actively participating in the TensorFlow community and forums, users can enhance their learning experience, receive support, and contribute to the growth and development of the TensorFlow ecosystem. Welcome to part 7, summary of what we have learned till now. So first part is more about wrapping up on the key concepts that we have learned. So let's go over the summary of each and everything that we learned till now. The first thing is tensors. Tensors are the fundamental data structures in TensorFlow, representing multidimensional arrays of numerical values. Scalars are zero-dimensional tensors, vectors are one-dimensional tensors, matrices are two-dimensional tensors, and higher dimensional tensors are arrays with more than 2 dimensions. Tensors can be constants, which are immutable, variables, which are mutable, or placeholders for input data during computation. The next concept was computational graph. TensorFlow uses a computational graph to represent mathematical operations as nodes and data flow as edges. Nodes in the graph represent operations such as addition, multiplication, and neural network layers. Edges represent the flow of tensors between operations, including the input-output relationships. The next concept, sessions. TensorFlow uses sessions to execute operations and evaluate tensors within a computational graph. Sessions allocate resources such as CPU or GPU and manage the execution of operations in the graph. Sessions are responsible for initializing variables, running operations, and releasing resources after computation. Next concept, variables and operations. Variables are mutable tensors that hold values that can be updated during computation. Operations are functions that take tensors as input, perform computations, and produce output tensors. TensorFlow provides a wide range of built-in operations for mathematical operations, neural network layers, optimization algorithms, etc. Next one, neural networks. Neural networks are computational models inspired by the structure and function of the human brain. TensorFlow enables the construction and training of neural networks for tasks such as classification, regression, and clustering. Common neural network architectures include feed-forward networks, convolutional neural networks, which are CNNs, recurrent neural networks, RNNs, and transformers. Next concept, training and optimization. Training involves iteratively adjusting the parameters of a model to minimize a loss function using techniques such as gradient descent and backpropagation. TensorFlow provides optimizers, loss functions, and metrics for training and evaluating machine learning models. Hyperparameter tuning, regularization, and early stopping are common techniques used to improve model performance and prevent overfitting. Next concept, deployment and serving. Once trained, TensorFlow models can be deployed for inference on various platforms, including servers, mobile devices, and the cloud. TensorFlow serving is a system for serving machine learning models in production environments, providing scalable and efficient inference capabilities. TensorFlow Lite enables the deployment of models on mobile and embedded devices with limited computational resources. Next concept is TensorFlow Extended, or TFX. TFX is a platform for building end-to-end machine learning pipelines from data ingestion to model deployment and monitoring. TFX components include data validation, pre-processing, model training, evaluation, and serving, facilitating the development and deployment of production-grade ML systems. Next concept is TensorFlow Quantum, or TFQ. TFQ is an open source library for quantum machine learning, allowing researchers and developers to build and train quantum machine learning models using TensorFlow. TFQ integrates quantum computing concepts and tools with TensorFlow's computational graph and optimization capabilities, enabling the development of quantum-enhanced machine learning algorithms. So just to summarize, TensorFlow is a powerful framework for building and training machine learning models, providing a wide range of tools, libraries, and functionalities for developing and deploying production-grade ML systems. Understanding key concepts such as tensors, computational graphs, neural networks, training, optimization, deployment, and specialization extensions like TFX and TFQ is essential for effectively using TensorFlow to solve real-world machine learning problems. In the next section, we're going to look at next steps in your TensorFlow journey. After familiarizing yourself with the key concepts and fundamentals of TensorFlow, here are some of the next steps to further advance your journey with TensorFlow. First, explore advanced topics. For this, dive deeper into advanced TensorFlow topics such as transfer learning and fine-tuning pre-trained models, hyperparameter tuning, and model optimization techniques. Advanced neural network architectures like attention mechanisms, transformers, and graph neural networks. Reinforcement learning, algorithms, and applications. Quantum machine learning concepts and algorithms. Next, experiment with TensorFlow add-ons and libraries. Explore TensorFlow's add-ons and additional libraries to extend TensorFlow's functionality. TensorFlow probability for probabilistic modeling and Bayesian inference. TensorFlow federated for federated learning and decentralized machine learning. TensorFlow recommenders for building recommendation systems. TensorFlow Model Garden for pre-trained models and model implementations. TensorFlow Hub for accessing pre-trained models and model components. Next, contribute to TensorFlow. You can contribute to TensorFlow open source community by submitting bug fixes, feature enhancements, and documentation improvements to TensorFlow's GitHub repository, participating in TensorFlow forums, discussions, and community events, even writing tutorials, guides, and blog posts to share your TensorFlow knowledge and experiences with the community, something like what I am working on here. Collaborating with other TensorFlow users and developers on projects, research, and initiatives. Next, you can work on some real-world projects which will give you real experience. Apply your TensorFlow skills to real-world projects and applications. Identify and define a machine learning problem or use case relevant to your interest or domain expertise. Collect and pre-process data, build machine learning models using TensorFlow, and evaluate model performance. Deploy and integrate your TensorFlow models into production environments or deploy them on mobile and embedded devices. Finally, iterate and refine your models based on feedback and insights from real-world usage. Next, continuous learning and professional development. Stay updated with the latest advancement in TensorFlow and machine learning by following TensorFlow's official blog, social media channels, and release notes for announcements, updates, and new features. Enrolling in advanced TensorFlow courses, workshops, and certifications to deepen your expertise and stay current with industry standards. Joining machine learning communities, attending conferences, and networking with other professionals in the field. Experimenting with emerging technologies and research areas related to TensorFlow, such as federated learning, quantum machine learning, and explainable AI. Next, share your knowledge and mentor others. Pay it forward by sharing your TensorFlow knowledge and expertise with others. Mentor aspiring machine learning practitioners and help them learn TensorFlow and navigate their own TensorFlow journey. Write tutorials, give talks, or contribute to educational resources to help others learn TensorFlow effectively. Collaborate on open source projects, research papers, or initiatives aimed at advancing the field for machine learning and TensorFlow. These are things that I would probably expect you to look at for next steps. By continuing to explore, experiment, contribute, and sharing your knowledge and experience with TensorFlow, you can further advance your skills, contribute to the TensorFlow community, and make meaningful contributions to the field of machine learning and artificial intelligence. Thank you for being here for this entire journey. And if you have any questions or any kind of queries, just please leave a comment below and we'll get back to you as soon as possible. Thank you again.